A man named Elliot arrived at a strange hotel that seemed to stretch endlessly along a road that had no end. He had been traveling for days and needed a place to stay. The sign above the hotel read, Hilbert's Grand Hotel. The name didn't mean anything to him, but the vacancy sign caught his eye. He went inside. The lobby looked normal. A single clerk sat at a desk. Elliot asked if there were any rooms available. The clerk said every room was occupied. Elliot turned to leave. The clerk told him to wait. Even though the hotel was full, they could make space for him. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries. Elliot was confused. He had just been told the rooms were all taken. The clerk explained the hotel had an infinite number of rooms, all filled. Room 1 was occupied, so was room 2, and so on forever. No empty rooms, but he could still be given one. The clerk picked up the phone and called room 1, telling the guest there to move to room 2. Then he called room 2, telling that guest to move to room 3. The process continued with each guest moving to the next higher numbered room. Every guest had a new room. Elliot was assigned room 1. He walked down the hallway. The door numbers increased without end. Room 1, room 2, room 3, room 4. Each room had a small plaque next to the door confirming its number. He reached room 1 and entered. It was simple but clean. He sat down, trying to understand what had just happened. He had arrived at a full hotel and still got a room. This hotel wasn't just a building. It was an idea made into a place. Elliot realized it didn't follow the rules he knew. In any normal hotel, once every room is taken, no more guests can be admitted. Here, full didn't mean what it normally did. If you have infinite rooms and they are all full, you can still move each person just one room over. Room N moves to room N+1. That frees up room 1. Even though there was no end to the rooms, they could still be shifted. Because infinity has no boundary, nothing stops the process. Later that evening, a bus pulled up outside the hotel. Elliot watched from the lobby window. The bus door opened and passengers poured out, one after another. Hundreds, then thousands. Elliot stepped outside. The bus stretched along the road, longer than anything he'd ever seen. It didn't stop unloading passengers. The clerk stepped outside too. Elliot asked how many people were on the bus. The clerk said infinitely many. Elliot asked how they could be accommodated. The clerk nodded and pulled out a notepad. He said each current guest would move from room N to room 2N. Guest in room 1 would move to room 2. Guest in room 2 would move to room 4, room 3 to room 6, and so on. Now, all odd-numbered rooms would be empty. An infinite number of new guests could fill them. Bus passenger 1 would get room 1, passenger 2 would get room 3, passenger 3 would get room 5, and so on. Each one found a room. Elliot followed the pattern. Every existing guest had been moved into even-numbered rooms. That freed every odd-numbered room. Since there are infinitely many odd numbers, there were enough rooms for an infinite number of new guests. The math was clear. Even when full, the hotel could still absorb infinity more. He walked back inside. The lobby was busier now, but there was still space. A second bus arrived. This one was labeled Infinity Squared. Elliot asked the clerk how many guests were on this one. The clerk explained there was an infinite number of buses, each with an infinite number of passengers. Every bus had a number. Bus 1, Bus 2, and so on. Each bus had seats labeled Seat 1, Seat 2, and so on. The guests were now coming in groups of infinity. Elliot asked how they'd be housed. The clerk said the hotel had infinite rooms, but that wasn't enough unless used carefully. If you try assigning Bus 1 to rooms 1 through infinity, then there's no space left for any other buses. That approach won't work. Instead, each guest would be assigned a room using a rule involving prime numbers. The clerk explained it slowly. Each bus number and seat number formed a pair. For guest in bus B, seat S, he assigned them to room 2B, starter 3S. Every room number became a product of powers of 2 and 3. This made every pair of numbers map to a unique room. No two guests got the same room. And since prime factorizations are unique, there would be no overlap. Elliot didn't follow every detail of the math, but he saw the result. Even with infinite buses carrying infinite passengers, everyone got a room. He leaned against a wall, staring down the hall. The idea began to settle. Infinity wasn't like a big number. It wasn't just a matter of size. It had structure. You could move it, stretch it, reshuffle it, and still never run out. That wasn't just strange, it was unsettling. It felt like a place without edges, a system without limits. More people kept arriving, and the clerk kept finding ways to fit them in. Elliot asked if the hotel could ever be truly full, in a way that no more could be added. The clerk said no. There was always a way. Infinity wasn't a container that overflowed. It was a process, a relationship. You could always find a place for more. Elliot returned to his room. He looked out the window. The night stretched on without end. Somewhere in the distance, he saw the glow of more buses arriving. The road didn't stop, neither did the hotel. He turned off the light. The hall outside hummed with quiet footsteps. Every room was full. Yet the hotel was never out of space. A man named Theo walks alone on a long road through an empty countryside. He carries a notebook filled with questions that keep him awake at night. Theo is a quiet man. He doesn't talk much, but his thoughts never stop. For years, he's wondered how infinity works. Not the kind of infinity where you keep counting forever. He means the kind that messes with your head, the kind you can't pin down. Today, he's thinking about numbers. Theo stops under a tree. The sun is low. He opens his notebook and stares at a page where he's written the first few whole numbers. 1, 2, 3, 4, 5, and so on. He flips the page and writes down all the perfect squares. 1, 4, 9, 16, 25. He knows how they go. Square a number, get a square. 2 squared is 4. 3 squared is 9. 4 squared is 16. It goes on forever, just like the whole numbers. Theo's curiosity grows. He asks himself how many perfect squares there are. He knows that for every whole number, he can square it and get a square. So if he lines up all the whole numbers in one column and all their squares in another column, he gets a 1-to-1 match. 1 goes to 1, 2 goes to 4, 3 goes to 9, 4 goes to 16. That's a perfect pairing. No leftovers, no missing values. The pattern is clean and complete. But then something starts to feel wrong. Theo circles the square numbers. He realizes they're spaced out more and more the higher they go. The gap between 1 and 4 is 3. Between 4 and 9 is 5, then 7, then 9. The jumps get bigger and bigger. Most whole numbers aren't perfect squares. Far from it. 95 isn't a square. 96 isn't either. Neither is 97, or 98, or 99. In fact, between 81 and 100, there's only one square. Just 2 perfect squares in a group of 20 numbers. That bothers Theo. He stands up and walks. He tries to reason it out. If perfect squares get rarer the further out you go, how can they be the same size set as the whole numbers? Most numbers are not squares, so how can they be matched up 1-to-1? There should be fewer of them. There should be missing spots in the square column. But there aren't. The pairing holds. For every natural number n, there's exactly one square n squared. And vice versa. The list never breaks. The match continues forever. Theo stops again. He thinks of someone asking him, how many whole numbers are there? Infinite, he says. Then how many square numbers are there? Also infinite. But is it the same infinity? He remembers the word countable. A set is countable if you can line up its members with the natural numbers. If you can list them, even if that list never ends. That's what he did. He paired 1 with 1, 2 with 4, 3 with 9. He built a list. That means square numbers are countable. So are natural numbers. They both stretch out forever. You can't say one is longer than the other if you can list them this way. He frowns. It feels wrong, like a trick. He looks at the ground and picks up a stone. He thinks about how in everyday life, more means more. 10 apples is more than 5. A dozen people is more than a pair. But in infinity, more doesn't always mean more. It depends how you count. And if you can count one set by mapping it exactly onto another, even if one seems to be only a part of the other, then by the rules of set theory, they are the same size. Theo looks back at his notebook. He draws a simple map. One arrow goes from 1 to 1, then from 2 to 4, 3 to 9, 4 to 16. He keeps going until the page runs out. The list never ends, but neither list has any leftovers. Every number in one list is matched with one in the other. No repeats, no gaps. That's enough. In set theory, that proves they're the same size. He turns the page and writes a sentence in plain words. There are just as many perfect squares as whole numbers, even though the perfect squares are only a part of the whole. He stares at that sentence. It breaks the rule of parts and wholes. If you have a basket of apples and you take some out, you expect fewer apples, not the same number. But infinity doesn't play by those rules. When Theo lines up the whole numbers and the squares, each number has a match. That means they're equal in size in the sense that matters to mathematics. The set of squares is a subset of the whole numbers, but the two sets are the same size when infinity is involved. Theo starts to walk again. He remembers reading that Galileo pointed this out centuries ago. Galileo noticed the paradox and didn't know how to resolve it. Back then, people didn't have modern set theory. Cantor hadn't yet defined what it means for two infinite sets to be equal in cardinality. Galileo thought maybe infinity wasn't a number at all, and that trying to treat it like one caused these strange results. Theo accepts it now, not happily, but calmly. He doesn't fight it anymore. He knows there are different rules for the infinite. In the finite world, parts are smaller than wholes. In the infinite world, a part can be just as big as the whole it comes from. You can remove most of the numbers and still have just as many left. You can take only the square numbers and still have a set that is the entire list of natural numbers. It's not a trick. It's not magic. It's just math. Strange, solid math. Theo doesn't try to resolve the discomfort. He lets it sit. He writes down one last line before closing his notebook. Infinity breaks the rules, but the rules are still true. Then he folds the page and keeps walking. A young woman named Mira walked the quiet corridors of the university library long after midnight. Her eyes scanned books on logic and math. Her hands traced diagrams and scribbled numbers across scratch paper. Mira was chasing a question she couldn't let go. It had started in her third-year set theory class, when her professor said that some infinities are bigger than others. The room had gone quiet after that. A few students laughed. Mira hadn't. The idea unsettled her. It stuck with her like a splinter under her skin. She had always thought infinity was just infinity. It stretched forever. It had no end. How could something that never ended be smaller or larger than another thing that also never ended? It didn't make sense. She wanted it to make sense. In one of the older sections of the library, she found a book with worn pages and faded print. It spoke of a man named Georg Cantor, who lived in the 19th century and made people angry by saying strange things about numbers. He claimed that there were different sizes of infinity. Cantor didn't just guess this. He proved it using something called the diagonal argument. Mira copied the steps into her notebook and began to test it in her own way. First, she listed the natural numbers, 1, 2, 3, 4, and so on. Each one had a place. They were infinite, yes, but she could count them one by one. That made them a countable infinity. If she had forever, she could read them all out loud. She could label each one with a number. The first natural number is 1, the second is 2. That's what made them countable. Then she thought about decimal numbers between 0 and 1, like 0.1, 0.42, 0.3157. These were real numbers. There were infinitely many of them too. But could she list them like the natural numbers? Could she match each real number with a natural number, one by one? She tried. She started writing decimal numbers in a list. 0.123456, 0.3333, 0.141414, 0.9999999.10110. Each number got a spot in the list. She kept going. She told herself maybe, if she were careful, she could get them all. Then she remembered Cantor's move. He said, even if you list the real numbers, no matter how long your list is, you will always miss some. The trick was simple. You look at the first digit of the first number, then the second digit of the second number, the third digit of the third number, and so on. You take each of those digits and change them. If the digit is a 1, make it a 2. If it's a 9, make it a 0. If it's a 5, make it a 3. It doesn't matter what the rule is, only that you change the digit. Then you take the new digits and form a new number. That number is not the first number because it differs in the first digit. It's not the second number because it differs in the second digit. It's not the third number or the fourth, or the fifth, and so on. The number you just made is different from every number in the list. But that's impossible. If your list had every real number between 0 and 1, then this new number should be in there too. But it isn't. That means your list was incomplete, always. No matter how carefully you build your list, no matter how long you make it, there will always be real numbers left out. There are too many of them. Too many to count, even with infinite time. That's what Cantor meant. The infinity of real numbers is bigger than the infinity of natural numbers. They are both infinite, but one cannot be matched with the other. They are not the same size. The natural numbers are countable. The real numbers are not. Mira sat with that for a while. It was strange. It felt backwards, but the proof held. She checked it again, made more lists, ran through more examples. She tried to beat the diagonal argument, but it always beat her. She thought about people lining up in an infinite queue. Each person had a name. You could call out their number and they would step forward. That was the natural numbers. Then she thought about a beach with infinite grains of sand, not just in number, but in position. Between any two grains, you could always find another. You couldn't number them. You couldn't list them all. That was like the real numbers. Even more strange, she realized there were more levels of infinity beyond that. The set of all subsets of real numbers was even bigger. That was the power set. And the pattern continued. Each time you formed a new power set, you created a larger infinity, an endless tower, one level above the next, going higher and higher without end. Mira didn't know whether to feel awe or fear. Infinity had once felt like a distant abstraction, like the word forever whispered into the dark. But now it had structure. It had shape. It had a hierarchy. Some infinities could be laid out in order. Others defied order entirely. She thought of how children learn to count. 1, 2, 3. It seems simple. Then they hear about infinity and think it's the final number, the biggest one. But it isn't. It isn't even a number in the usual sense. It's a process, a direction, a never-ending path. And Cantor showed that some of these paths fork, and one branch spreads wider than another, and some are so wide you can't even name the steps. She scribbled one last line in her notebook. The natural numbers fill up a list, the real numbers spill off the page. Mira stood up, closed the book, and stepped outside. The sky above her was full of stars, spread across the black like real numbers between 0 and 1. There were too many to count. Even with infinite time, some would always remain unnamed, unlisted, unknown, and yet they were there, waiting. A man named Elliot lived alone in a small room above an old library. His days passed quietly, flipping through books most people had forgotten. He worked as a part-time cataloger for the university, sorting through new arrivals and digitizing records. It was the kind of job that let him think too much, and Elliot liked to think. One morning, he opened a package. Inside was a single folder. No book, no cover, just loose pages. At the top of the first sheet, in faded ink, it read, "The set of all sets that do not contain themselves." Elliot stared at it. Then he read the line again. The language was precise. There was no introduction, no explanation. It simply defined the set. It included all sets that do not include themselves as members. He pulled a pad from his drawer and scribbled down examples. A set of apples doesn't include itself. A set of animals doesn't include itself. These seemed simple. The set of all things in his kitchen. That's not a member of itself. That made sense. Then he tried to test the idea further. What if a set does contain itself? He imagined one. A set of all abstract concepts, maybe. That could include itself, since abstract concepts might include the idea of sets. But it was slippery. Still, he stayed focused on the first case. Sets that don't contain themselves. He made a small list. The set of all chairs, the set of all birds. The set of all things that are not red. None of those include themselves. Each seemed safe, but then he tried to collect those safe sets. He wrote, "Let R be the set of all sets that do not contain themselves." That's when the problem arrived. He paused, looked at the line, and read it out loud. If R is the set of all sets that do not contain themselves, then does R contain itself? He stood up, walked to the sink, and ran cold water. It was like the words were chasing themselves in circles. He went back to the desk. Suppose R does contain itself. That would mean R is one of the sets that do not contain themselves. But that's a contradiction. If R contains itself, then by definition, it shouldn't be in the set, because the set only contains sets that don't contain themselves. But now, suppose R does not contain itself. Then according to its definition, R should include itself, because it's a set that doesn't contain itself. That also leads to a contradiction. Eliot sat down, slower this time. He reread the sentence. Then he stared at it. The logic loop had no clear way out. The more he thought, the more it twisted. Each time he tried to resolve the contradiction, it folded back in on itself. He turned to his old logic textbook. In it was a chapter about Bertrand Russell and how this very problem disrupted early set theory. Mathematicians had once believed that any collection could be treated as a set. You could make a set of all books, or all numbers, or all sets. There was no reason to doubt it. It felt clean, logical. But then Russell introduced this problem, the set of all sets that do not contain themselves. Does it contain itself or not? Either answer leads to a contradiction. You're trapped. The structure collapses. Eliot drew a circle on the pad. He labeled it R. Then he drew arrows going in and out of the circle. The arrows tangled. No direction held up. The paradox was simple and sharp. It didn't need complex math. Just a definition, then a question. He tried to apply the idea to something outside of math. Could this happen in language? Could it happen in behavior? He imagined a small village. In that village, there's a barber. The barber shaves all men who do not shave themselves. Who shaves the barber? He nodded. That's the same structure. If the barber shaves himself, he shouldn't shave himself. But if he doesn't, then by the rule, he should. It's the same loop. Eliot began writing notes. The issue wasn't just about sets. It was about self-reference. When a system refers to itself, it risks folding into paradox. Like a sentence that says, "This statement is false," it has no stable truth value. He remembered another example, a library catalog that tries to list all catalogs that do not list themselves. Should it list itself? If it does, it breaks its own rule. If it doesn't, it also breaks the rule. The act of including or excluding triggers the contradiction. This kind of paradox, Russell's paradox, showed that naive set theory couldn't hold. There had to be limits. Rules had to be defined more carefully. Not every collection could be a set. Some ideas had to be excluded to protect the structure. Eliot looked back at the folder. He realized it wasn't just a fragment from a math text. It was a warning, a quiet one, about how systems behave when they try to include everything. Total inclusion leads to collapse when self-reference enters the loop. He looked out the window. The sun was fading. Somewhere below, a delivery truck rumbled past. He felt the stillness of his room again, but it no longer felt steady. Even in this small space, even in this quiet job, there were ideas that broke things apart. He returned to the pad and underlined a phrase, "Not every container can contain itself." He thought about programming languages, about infinite loops, about logical rules in software that must avoid circularity. He thought about social rules too, about communities that try to define who belongs, who doesn't. What happens when the rule starts to judge itself? The pattern wasn't confined to logic. It echoed in systems everywhere. He flipped the folder shut, placed it on the corner of the desk. He didn't feel finished, but he no longer felt lost. The paradox wasn't there to be solved. It was there to be seen. The next morning, Eliot returned to the library. He cataloged 3 more books, checked the digital archive, and logged a shipment. In the break room, someone asked him why he looked tired. He shrugged and said, "Too much thinking." But the paradox stayed with him. Quiet and precise, a set that cannot hold itself, a circle that eats its own tail, a rule that folds when it touches itself. Not a riddle to be solved, a boundary to be respected. A man named Elias walks through a quiet forest on a cold morning. He's a mathematician, the kind who lives for abstractions, and he's thinking about space. Not outer space, but space as in geometry, volume, and shape. He's thinking about how things fill space, how a cube holds volume, how a balloon traps air. Then he remembers a strange idea he read in a journal once, the Banach-Tarski paradox. It stayed with him because it didn't make sense. It said you could take a solid ball, split it into a few pieces, and put those pieces back together into 2 balls of the same size as the first. The idea sat in the back of his mind like a riddle no one should try to solve. Elias returns to his small home and goes to his desk. He draws a circle, then tries to imagine cutting it up, but in a simple, practical way. He thinks about slicing an apple and placing the pieces into another apple shape, but he knows this isn't what the paradox is about. It isn't about physical cutting. It's not something you can do with knives or scissors or lasers. The pieces in this paradox are strange. They don't behave like normal objects. They don't have edges in the way we understand edges. He looks again at the original statement. A sphere in three-dimensional space can be divided into 5 disjoint sets. Using only rotations and translations, you can rearrange those sets into 2 spheres identical to the first. Nothing gets stretched, nothing gets squished, no volume is added, yet the result is double what you started with. He walks to the kitchen and picks up a rubber ball. He holds it in his hands. He squeezes it. It's solid, real, finite. But the paradox says that if you follow the rules of certain kinds of infinite math, you can break this single ball into a few parts, move those parts around, and end up with 2 balls, both the same size as the one in his hand. The key to this paradox is in something called the axiom of choice. Elias knows this term. It's a principle in set theory that allows you to select elements from sets, even when there's no clear way to do the selecting. Imagine you have an infinite number of drawers, and each drawer has a pair of socks. The axiom of choice says you can pick 1 sock from each drawer to form a new set. That sounds reasonable. But now scale that up. Apply that to points in space. Instead of socks in drawers, think of choosing 1 point from each group in a massive, unstructured cloud of points. There's no rule telling you how to choose. The axiom just says you can. Elias returns to the problem. In the Banach-Tarski paradox, the pieces you break the sphere into aren't like apple slices. They're abstract sets of points. These sets are non-measurable. You can't assign them a volume. They aren't solid. They don't have well-defined shapes. They exist because the math says they can. And using the axiom of choice, you can pull them apart in a very specific way. He writes out a basic version of the process. You start with the sphere, you break it into 5 groups. You rotate and shift these groups through space. You reassemble them. Somehow you have 2 spheres, each the same size as the first. Nothing gets created, nothing gets destroyed, and yet you've doubled what you had. Elias knows this violates conservation of volume, at least in the physical world. But in pure math, volume isn't conserved in the same way. He thinks back to Hilbert's hotel, another infinite paradox. A hotel with infinite rooms is full, but it can still accept new guests by shifting each current guest 1 room over. Infinity bends logic. The Banach-Tarski paradox uses that same bending. It works because of the strange behavior of infinity in 3-dimensional space. Elias draws 3 axes, x, y, z. He places a sphere in the middle. He tries to imagine selecting points from the surface of that sphere using the axiom of choice. He imagines decomposing the sphere not into chunks but into clouds of points, scattered yet exact, chosen with no pattern but still distinct. He tries to imagine rotating these clouds, each built from an infinite number of non-measurable points, and placing them back together. It bothers him. The math is sound, but it defies everything he knows about the real world. In the physical world, atoms have volume. You can't split something into nothing and end up with more of it. But Banach-Tarski doesn't work in the physical world. It only works in the abstract world of mathematics. You can't build a machine to perform this paradox. You can't hold one of these pieces in your hand. They only exist in the realm of infinite sets. He picks up a deck of cards and shuffles it. This reminds him of how important order and selection are in the paradox. If you don't use the axiom of choice, you can't pick the right pieces. And without those pieces, the whole trick falls apart. It's like having a key to a lock, but the key is made from pure theory. He remembers that the paradox only works in 3 dimensions or higher. In 2 dimensions, something called the Hausdorff paradox prevents it. The world of the paradox changes with space itself. In lower dimensions, these decompositions don't exist. But in 3D space where we live, the paradox becomes real. Real in math, not in matter. Elias understands now. The paradox doesn't say you can physically duplicate a ball. It says that in the world of infinite sets and point-based geometry, our rules about size and volume break down. Our normal idea of what it means to split something and reassemble it stops working. Infinity doesn't care about physical intuition. He sets the rubber ball back on the table. It remains whole, real, untouched. It doesn't split, it doesn't double. But the idea that it could, in some higher form of mathematics, lingers in the room like a strange scent. The Banach-Tarski paradox is a reminder that math isn't limited by the world we live in. It follows its own laws, and sometimes those laws produce results that look like magic. But they're not magic. They're logic, extended to its infinite limits. He writes a note to himself on the edge of a napkin. Not all infinities are the same, and some break the rules we thought were unbreakable. Then he folds the napkin, places it under the ball, and walks back into the forest. The paradox stays behind on the desk, settled but unsolved. A young woman named Lena walks through a long corridor. She wears a light jacket and carries a journal in one hand. The corridor is empty. It stretches ahead, quiet and lit by a soft, consistent light. She begins at one end and walks toward a door at the far end. A voice speaks. Lena takes her first step. She covers half the corridor. She stops. She looks down at the ground beneath her feet. She walks again. She covers half of the remaining distance. She stops again. Less ground remains, but she's not at the door. She repeats this, half again, stops, again and again. Each time she moves, she only goes halfway. The gaps between her and the door get smaller. First 10 meters, then 5, then 2.5, then a little more than a meter, then 50 centimeters, then 25, then 12. The process continues. This is Zeno's dichotomy paradox. It states that to reach any destination, you must first get halfway there. But once you reach halfway, you still have to go half the remaining distance, and half of that, and so on. If every movement is divided like this, then there are an infinite number of steps between any 2 points. Lena is not lost. She understands where she is. The door is in front of her. She knows her goal. But this paradox suggests that movement is impossible. If you must complete an infinite number of steps to reach the door, how do you ever get there? Lena sits on the floor. She takes out her journal. She writes what she knows, a step forward, halfway, half of that, and so on. Infinity. That's the problem. Not the distance, not her legs, not her will. Infinity appears to make the task impossible. The corridor is finite, it's 30 meters long. But between any 2 points, between any 2 centimeters, there are infinite midpoints. That's what the paradox suggests. If she must cross an infinite number of steps, and if each step takes some time, then how can she ever finish? She watches the light reflect on the floor. Her breath is calm. She does not panic. She thinks through the paradox. Suppose each step takes her 1 second. First, half the corridor in 1 second, then half the remaining in 1 more second. But that sequence doesn't match what happens in real life. She remembers something else, a math lecture from years ago. The sum of an infinite series can still be finite. She picks up her pen and writes, 1/2 plus 1/4 plus 1/8 plus 1/16. This series goes on forever. Each number is half the previous one, but the total of all these numbers is 1. That's the key. She realizes what's wrong with the paradox. It assumes that infinite steps mean infinite time or infinite effort, but that's not the case. The steps get smaller and smaller. The time for each gets shorter and shorter. The total time or total distance can still be finite. She closes her journal and stands up. The paradox lives in the world of logic and language. In reality, her legs do not stop her with every fraction of a step. Her body is not limited by mathematical infinities. She walks. The atoms in her body interact. Her muscles contract. The floor gives way to her weight, and she moves. Lena walks again. This time, she doesn't stop halfway, but the logic still holds. Each part of her journey still includes a halfway point. It's always there, but she no longer sees it as a barrier. She knows that infinite does not mean unreachable. She walks forward. Mathematics allows for infinity, but it also knows how to handle it. Calculus, developed long after Zeno's time, provides the tools. Integrals and limits show how infinite processes can lead to finite results. Zeno's argument is sound from a certain angle. If you treat every step as an independent motion, and if each takes a set amount of time, you get trapped. You never reach the end, but when you allow for limits, the paradox dissolves. The problem is not physical, it's conceptual, it's in the framing. Lena reaches the door. She touches it, pushes it open. The paradox did not stop her. It only asked her to think. Zeno, a philosopher from ancient Greece, meant this paradox to challenge assumptions. In his time, the concept of motion was deeply tied to perception. He believed the world might not be as it seems. He posed the paradox to show that our understanding of space, time, and motion might be flawed. Today, we see Zeno's dichotomy not as a barrier, but as a doorway, a moment to reflect on how infinite processes can be part of the finite world. Lena steps through the door. On the other side is a wide-open space, trees, wind, and sky. She walks across the grass. Every movement contains infinite midpoints, but she does not stop. She moves because motion is real. The paradox is not about whether she can reach the tree across the field. She will. She does. The paradox is about how we describe that motion and how our language can sometimes tie us in knots. She remembers how she used to think about infinity as unreachable, like something too big to understand. But now she knows that infinity isn't always a size. It's a process, a concept. It can fit inside a second. It can exist in a centimeter. She touches the bark of the tree. The paradox has taught her something. That motion is not just steps. It's not just parts. It's a whole. And sometimes to understand the whole, you need to let go of the parts. She walks away, not counting the steps. Achilles stands at the starting line, muscles coiled, eyes focused. The sun is low behind him. A tortoise waits 50 meters ahead, its shell catching the light. A race is about to begin. Achilles, the fastest man in Greece, gives the tortoise a head start as a gesture of confidence. After all, how could he not overtake a slow-moving reptile? The race starts. Achilles sprints forward. He quickly covers the distance to where the tortoise began. But in the time it takes him to get there, the tortoise has moved a little farther. Not much, maybe 5 meters. Achilles reaches that point too. But the tortoise has moved again, perhaps just 1 meter now. Achilles runs again, reaches that point, and the tortoise, though crawling, has moved again, this time only a fraction of a meter. This continues, again and again. Every time Achilles reaches where the tortoise has moved forward. The gap keeps getting smaller, but it never seems to disappear. Zeno of Elea proposed this paradox in ancient Greece. He wanted to challenge the concept of motion itself. He used logic to trap Achilles in an infinite number of steps, even though we know from experience that Achilles would quickly pass the tortoise. Zeno's reasoning works like this. Before Achilles can overtake the tortoise, he must reach the point where the tortoise started. But by the time he gets there, the tortoise has moved. Achilles must then reach this new point. Again, the tortoise has moved. This creates an infinite sequence of tasks. Since there are infinitely many points Achilles must reach, Zeno argues that Achilles can never pass the tortoise. In the story, Achilles becomes a symbol for speed, power, and certainty. The tortoise stands for slowness, stubbornness, and paradox. In Zeno's logic, speed doesn't win, infinity does. To understand how this works, picture a movie playing frame by frame. At each frame, Achilles moves closer to the tortoise, but there's always one more frame to go before he passes it. It seems like no matter how fast he moves, there's always another frame, another step, another gap. That's the trap of the paradox. It breaks motion into infinite parts and then says they can't all be completed. But in real life, Achilles does pass the tortoise. So where's the flaw? To see it, imagine measuring the distances Achilles must run in each step. First, he runs 50 meters, then 5, then 1, then 0.2, 0.04, 0.008, and so on. The distances shrink fast. Add all these up, and you get a total distance that's a little more than 50 meters. The total time it takes Achilles to run these distances is also finite. That's because the time intervals shrink too, just like the distances. If he runs at 10 meters per second, the first leg takes 5 seconds, the next half a second, then a tenth of a second, and so on. Add all these times together, and you still get a finite number. Maybe just over 5.5 seconds. So while there are infinite steps in theory, they don't take infinite time in practice. That's the key. Infinity doesn't always mean something goes on forever in reality. It means the steps can be split endlessly, but the sum of those steps can still be a limited number. Mathematicians call this a convergent series. Achilles' mind can't see the finish line in Zeno's setup because Zeno keeps moving the goal. But time doesn't work that way, neither does motion. Infinity is a concept, not a physical barrier. Achilles doesn't stop at each point waiting for the tortoise to move. He runs through the space in one smooth motion. Time doesn't pause for logic. It flows. And Achilles flows with it. Zeno's paradox works like a mirror maze. Every time you think you're out, you find another turn. It uses logic to challenge what your senses know to be true. You've seen people pass others in races. You know Achilles would beat the tortoise. But Zeno's argument slows that moment down and asks what happens in each instant, in each point. It turns something simple into something impossible. This story isn't really about Achilles. It's about how we understand movement, space, and time. Zeno shows that if you think about motion as a series of discrete steps, and you believe each step must finish before the next begins, you trap yourself in an infinite loop. You break motion into stillness and then ask how stillness can move. Modern physics and mathematics moved past this problem with the development of calculus. Isaac Newton and Gottfried Leibniz created tools to handle infinity in a new way. They showed how an infinite number of very small quantities could add up to a finite result. Calculus defines limits. It says you don't need to finish an infinite sequence of steps one by one. Instead, you can measure the total effect as those steps become infinitely small. This approach breaks Zeno's paradox. It accepts infinity, but it doesn't let it rule. If Zeno were alive today, he might still argue. He wasn't just playing a math game. He was making a point about the limits of human understanding. He believed that reality wasn't what it seemed. He thought the senses were misleading. If motion leads to contradictions, maybe motion itself is an illusion. That was the deeper claim. But our protagonist Achilles isn't interested in metaphysics. He runs. The tortoise inches forward. In seconds, Achilles catches up. He passes. He wins. Zeno watches from the sidelines. His logic stands untouched, but so does Achilles' victory. Both are true in their own worlds. One is made of thought, the other is made of time. This tension between reason and experience continues. We still use Zeno's questions to explore the edge of understanding. Achilles still runs, not just on the track, but through every problem where infinity hides. The tortoise still moves, not fast, but forever just ahead in the logic of paradox. What Zeno did was simple and strange. He slowed down the world until it broke. Achilles fixes it again by simply doing what people do, moving forward. That's the quiet power of motion. It doesn't argue, it proves. A chimpanzee named Coco sat in a quiet lab on the edge of town. The room was simple, white walls, a single desk. On the desk sat a typewriter. Next to it, a bowl of bananas. Coco had no idea what the typewriter did. He only knew that pressing the keys made satisfying little clicks, and sometimes a sheet of paper slid out with markings. Coco wasn't trained. He wasn't taught what letters meant. He wasn't aiming to write anything. He just pressed keys when he felt like it. Sometimes with his fingers, sometimes with his toes, once with his nose. He pressed them at random. No sequence, no structure, just instinct. Scientists watched through a glass wall. They weren't watching for fun. They had a theory. It was called the infinite monkey theorem. It said that if you gave a monkey a typewriter and an infinite amount of time, eventually the monkey would write the complete works of Shakespeare. Every sonnet, every act, every comma, exactly as it appeared in print. Not almost Shakespeare, not something like it, the real thing. Word for word. This idea sounds wrong. It goes against what feels reasonable. A monkey doesn't know what writing is. It doesn't know grammar or rhythm or rhyme. It doesn't care about soliloquies or kings or tragedies. But the theorem doesn't rely on understanding. It relies on math. It relies on probability. And probability, when given infinite time, does strange things. In the beginning, Coco pressed keys without meaning, a string of X's, then some jumbled consonants, then somehow to be. But it wasn't followed by or not to be. It was followed by uoi puar, gibberish, noise. But the phrase to be stood out on the page, like a fluke, like lightning striking. The scientists marked it down, a statistical blip. To understand why this happened, you need to think about combinations. If a typewriter has 50 keys and Coco hits 1 key per second, every second a new character appears. The chance of typing a specific word like the is 1 in 125,000. It's not impossible, just rare. As time passes, even rare things happen, and with enough time, they happen again. 1 week in, Coco had filled dozens of pages. Most of it made no sense, but here and there you'd see something odd, a full sentence, a fragment that looked like a quote. Not Shakespeare, not yet, but signs of structure, like finding the shape of a fossil in a pile of rocks. Let's pause and imagine this differently. Imagine flipping a coin, heads or tails. Easy enough. Now imagine flipping that coin forever. Eventually you'll see 10 heads in a row, maybe even 100. It might take years, but it'll happen. Not because of magic, because with infinite tries, everything possible must happen eventually. Now, scale up. Instead of 2 outcomes like a coin, imagine 50 keys on the typewriter. The number of possible combinations of letters grows fast. To type just one line from Hamlet correctly, like to be or not to be, requires pressing the right keys in the exact order. That's around 18 characters, including spaces and punctuation. The number of possible 18-character strings from a 50-key typewriter is 50 to the power of 18. That's a number with 30 digits, a 1 followed by 30 zeros. Massive, but not infinite. If Coco kept typing 1 character per second, he'd need more time than the universe has existed to get that exact line. But if he had infinite time, the moment would come. That's the heart of the theorem. Back in the lab, months passed. Coco showed no signs of learning. That was expected. Learning wasn't required. He kept pressing. Letters, more letters, sometimes numbers. Sometimes he hit return and a new line began. The machine didn't care. It recorded everything. One day, a graduate student reviewing the pages stopped. He read a sentence aloud. Then again, it was a line from Macbeth. Not exact, but close, off by 1 word. Then he found another line, this time from King Lear. Again, not perfect, but close. He marked them with a pen and moved on. This brought up another point, near misses. In an infinite sequence, near misses happen more often than exact matches. You get to be or not to be, but with 1 typo, or missing punctuation, or reversed words. These near matches are common. Exact matches are rare, but not 0. And given infinite time, exact matches must occur. They must. Probability demands it. If you write every possible string of letters of every length, somewhere in that list is Hamlet. Somewhere else is Macbeth. Somewhere else is a perfect transcription of the sonnets, complete with formatting. Somewhere else is a version of Hamlet where every character's name is changed. Somewhere is a version where Hamlet ends with a wedding. Every possible variation exists. Every possible text. Every book ever written. Every book never written. This isn't just theory. Mathematically, the set of all possible strings is countably infinite. That means we can assign a number to each one and list them. And in that infinite list, every finite text must appear. The infinite monkey theorem doesn't mean a monkey will write Hamlet quickly. It doesn't mean it'll happen soon. It means that given unlimited time, the outcome is not just possible, it's inevitable. That's the paradox. It feels impossible, but it's guaranteed. Coco kept typing. He never stopped. Every new key was a new path, a new chance. Most led nowhere, but some led to fragments of meaning. Some led to sentences. Some, someday, would lead to Shakespeare. That was the unsettling truth. Meaning could emerge from randomness. Order could rise from chaos. Not by design, but by sheer scale. Not by intelligence, but by repetition. One afternoon, a technician walked in and looked at the latest page. He read, "Thus conscience does make cowards of us all." He checked the original text. It was exact. The technician didn't cheer. He didn't call the others. He just stared. Then set the page aside. He knew it would happen again and again and again, because infinite time makes the improbable certain. Theo was a grad student in mathematics. He spent most of his time in the university library, buried in books filled with symbols, sequences, and proofs. He liked patterns. They gave him a sense of order. Equations made sense to him in a way that conversations often didn't. He liked numbers that got smaller. He trusted things that tapered off. One day, his professor handed him a problem to write about. It looked harmless at first. 1 plus 1/2 plus 1/3 plus 1/4 and so on, forever. The harmonic series. Theo had seen it before. He knew the rule. Keep adding the reciprocal of every natural number. It looked like it should settle down. Each term shrank. Each new number added less than the one before. It felt like the sum should eventually stop growing, but it didn't. That's what made it strange. He remembered reading that the harmonic series diverges. That meant it keeps getting bigger and never stops. No matter how many terms you add, the total keeps increasing without bound. Even though each term becomes tiny, the overall sum does not level off. He couldn't accept it right away. He wanted to see it for himself. He sat at his desk and wrote out the first few terms. 1 plus 1/2 is 1 1/2. Add 1/3 and you get 1 5/6. Add 1/4 and you reach a bit more than 2. Keep going with 1/5, 1/6, 1/7. The numbers added less and less, but the total kept creeping up. To test it, he opened a spreadsheet and added the first 1,000 terms. The total was somewhere around 7, still not that big. But when he added 10,000 terms, it was closer to 10. He tried 100,000. It kept going. The growth was slow, but it never stopped. That was the point. The series didn't blow up quickly. It wasn't like adding 1 + 2 + 3, where you could see it growing without end. The harmonic series was subtle. It looked innocent. But given enough time, it became infinite. Theo remembered a classroom explanation that had stuck with him. You group the terms in a clever way. The first term is 1, the next term is 1/2, then you group 1/3 and 1/4 together. That's more than 1/2. Then you group the next 4 terms, 1/5, 1/6, 1/7, 1/8. Together, those also add to more than 1/2. Keep going. Group the next 8 terms. Again, their total is more than 1/2. Each group of terms doubles in size, but the total of each group stays above 1/2. So you get 1 + 1/2 + 1/2 + 1/2 again and again. No matter how far you go, you keep adding another chunk larger than 1/2. That never stops. So the whole sum grows without bound. It diverges. This kind of thinking made Theo pause. It wasn't just about the numbers, it was about the structure. The way you grouped them revealed something the raw sequence didn't. That trick showed the truth of the matter. Shrinking terms don't guarantee a shrinking sum. He tried explaining it to a friend who studied engineering. She shrugged and said, if the numbers get smaller, the total should settle down. That was the common belief. It made intuitive sense. But the harmonic series broke that assumption. He thought about it another way. Imagine a glass that holds water. You pour in 1 liter, then you pour in 1/2 liter, then 1/3 liter, then 1/4. At some point, you'd expect the glass to overflow. The catch was how slowly it would happen. You could pour forever, but the glass would still take in more water, just at a snail's pace. That was the idea behind the series. It diverged, but it did so reluctantly. Theo kept reading. He found that this series came up in real problems, in physics, in number theory, even in analysis of algorithms. Computer scientists studied the time it took for certain processes to complete, and sometimes the harmonic series showed up in the results. That was surprising. A sum that grew so slowly could still matter. He started to see a pattern in nature and in data. Some processes never quite stop. They slow down, but they keep moving. A decaying echo, a vibrating string, a system that leaks energy but never goes still. The harmonic series reminded him of those systems. He imagined a runner on a track. She runs 1 kilometer, then 1/2 kilometer, then 1/3. Each time the distance shrinks, but she keeps running. The total distance grows, not quickly, but without end. If she keeps running forever, she covers an infinite distance. Not because her steps are long, but because there are so many of them. Theo tried to prove it again. He looked at the integral test. The integral of 1/x from 1 to infinity diverges. That matched the harmonic series. The graph of 1/x falls gently, but the area under the curve keeps growing. That was another view of the same truth. Different method, same result. He started seeing comparisons. He looked at the series of 1/n². That one converged. The terms in that series got small fast enough. The total stayed finite. That's where the line was drawn. If you drop off just a bit faster, the infinite sum behaves. But if you only fall off like 1/n, it escapes control. He ran simulations. He wrote code to test different series. 1/n to the power of 1.1. That converged. 1/n to the power of 0.9. That diverged. He adjusted the exponent by tiny amounts and saw the difference in growth. The harmonic series became a kind of border, a threshold between series that settle and those that don't. It was a slow-motion infinity, a creeping expansion. Theo liked how it didn't look infinite, but it was. It taught caution. It showed that you couldn't trust your first impression. Just because something shrinks doesn't mean the total won't explode. He thought about paradoxes again. The harmonic series wasn't flashy like a contradiction. It wasn't a puzzle with a twist. It was steady, patient, and unforgiving. It broke expectations in plain sight. That made it powerful and unsettling. He walked through the math building late one night. He passed a whiteboard filled with equations from another class. Most of them were familiar, but one line caught his eye. It just said 1 + 1/2 + 1/3 + 1/4, and so on. No equals sign. No sum, just the series, like an open door. He picked up a marker and added 2 words under it, diverges slowly. He capped the pen and walked away. A man named Caleb lived by the coast. Every morning, he walked to the same stretch of beach and watched the tide roll in. He liked quiet places and small routines. He also liked puzzles, not the kind with pieces, but the kind that made you think about how things are defined. One day, while walking along the sand, he came across a small hill of it, a mound shaped by the wind and the footsteps of people passing by. It wasn't huge, but it was bigger than a pile. It looked like a heap. He stood there and stared at it. Then he bent down and took 1 grain of sand from the top. It was still a heap. He picked up another grain, still a heap. He kept going, 1 grain at a time. Caleb knew what he was doing. He was testing an idea called the Sorites Paradox, sometimes just called the Heap Paradox. It starts with a question that seems simple. If you remove 1 grain of sand from a heap, is it still a heap? Of course it is. 1 grain doesn't change anything. But what if you do it again and again? If removing 1 grain never makes a difference, then you should be able to remove every grain without ever losing the heap. But at the end, you're left with nothing. Clearly, nothing isn't a heap. That's the problem. The paradox sits in how we use words. A heap is not a fixed number. There's no rule that says a heap starts at 1,000 grains or ends at 100. The word is vague. It depends on context, on perception, and sometimes on opinion. But in logic, even small vagueness can cause big problems. Caleb crouched beside what was left of the mound. He had removed a few handfuls of sand now, maybe a few hundred grains. It still looked like a heap, just a bit smaller. He imagined a chart in his head. On one side, the number of grains. On the other, whether people would still call it a heap. At 100,000 grains, everyone says yes. At 50,000, most people still agree. At 10,000, maybe some begin to hesitate. At 1,000, it gets tricky. At 500, it starts to look more like a pile. At 100, it's probably just sand. At 10, no one would call it a heap. But where is the exact point when it changes? That's the core of the paradox. Each small change seems harmless. Removing 1 grain never feels like it matters. But if you keep going, you reach a result that clearly conflicts with the starting point. The same logic applies to other things. At what point does a person with a full head of hair become bald? 1 hair doesn't matter, nor does 2. But somewhere in between full and bald, there's a shift. But you can't pin it down to a specific number without being arbitrary. Caleb once read about a farmer who used this thought puzzle to talk about trust. If you always tell the truth, you're honest. If you tell 1 small lie, most people still think you're honest. What about 2 lies? What about 10? At what point do you stop being trustworthy? The logic becomes slippery. Back on the beach, a child ran past the place where Caleb sat. The child didn't notice the shrinking mound. To the child, it was just sand. Caleb wondered how many grains he had moved. 1,000? Maybe 2? He hadn't counted, and it didn't really matter. The problem wasn't in the number, it was in the transition. He thought about definitions. Maybe the issue was that the word heap didn't have a clear one. In mathematics, things are exact. 2 + 2 is 4, always. In formal logic, every term needs to be precise. But in everyday language, words like heap, tall, bald, rich, and old, helder don't come with strict boundaries. They shift depending on who is using them. Some philosophers tried to fix this by introducing something called fuzzy logic. In fuzzy logic, you don't just say something is true or false, you say how true it is. For example, maybe having 500 grains of sand is 80% heap. Maybe 200 grains is 30% heap. It doesn't solve the problem in the strictest sense, but it helps describe the transition more smoothly. Caleb didn't care much for fuzzy logic. He liked sharp lines and clean answers. But this paradox wouldn't give him that. It kept circling back to the same point. The way we describe the world is often more flexible than we want it to be. He looked down again. The heap was now just a small rise in the sand. No one would stop and notice it. It had become ordinary. At some point in the process, it stopped being a heap. But he couldn't say when. He could guess. He could point. But he couldn't prove it. This wasn't just a puzzle about sand. Caleb saw it everywhere. Laws were written in words, so were contracts, promises, and instructions. If a rule said a person must be adult, does that mean 18 years and 0 days? What if someone is 17 years and 364 days? Does that one day make a difference? Most rules had to draw lines somewhere, but the lines always left questions on either side. He once heard someone say, "A little bit wrong is still wrong." That made sense until you tried to use it in real life. A road speed limit might be 60 miles per hour. Is 61 wrong? Is 60.5? What if the driver glances at the speedometer and it flickers between readings? Is that enough to punish someone? Most people agree there's a gray area. The Sorites paradox lives in that gray area. Caleb scooped the last of the small mound into his hand. It didn't feel like anything special now. It was just sand. He let it fall through his fingers. Each grain was nearly weightless. On its own, each one meant nothing, but together, they had formed something worth noticing. That was what made the paradox strong. The sum was real, even when each part seemed insignificant. He brushed off his hands and stood up. He knew the paradox didn't have an easy answer. It wasn't meant to. It was a mirror. It showed how much we relied on unclear language and smooth transitions in a world that sometimes demanded sharp divisions. The puzzle didn't lie in the sand. It lay in the space between when something was still a heap and when it was not. In that space, logic and language drifted apart. He walked back down the beach, thinking not about sand, but about how often he'd used words like a lot, a few, barely, and almost. Each one carried its own version of the heap problem. Each one asked the same question without ever answering it. Caleb didn't mind. Some puzzles didn't need solving, they only needed noticing. Cale spent most of his time alone in the university library. He was studying logic, not just how arguments worked, but the kind of logic that unraveled when you pulled at the wrong thread. He liked puzzles, not the kind with pieces, but the ones made of language. His professor said he had a mind for contradictions. He agreed. One day, while reading an old paper on semantic paradoxes, Cale came across a single sentence printed in bold. "This statement is false." At first, it looked like a joke. A sentence talking about itself wasn't unusual, but this one didn't give any ground. It said what it was, and it said that what it was wasn't. He read it again, then again. Each time it spun in place like a coin refusing to fall. He picked up his notebook and wrote it down. "This statement is false." Then he tried to assign it a truth value. If the sentence is true, then what it says must hold. But it says it is false. So if it is true, then it must be false. That didn't make sense. Then he tried the opposite. If the sentence is false, then what it says must not be true. But it says it is false. That would mean the sentence is not false, which would make it true. So if it's false, it must be true. If it's true, it must be false. Cale stared at the words. They didn't move. But the meaning slipped out from under him like the ground shifting without warning. It was the kind of paradox that didn't rely on numbers or infinity. It was made of nothing but ordinary language. He spent the next few days thinking about how something so small could break the entire structure of logic. This wasn't a grammar mistake. The sentence was complete and clear. It followed the rules. That made it worse. A broken thing that looked perfectly intact. To understand it better, Cale tried to build a scenario. He imagined a machine. The machine's only job was to sort sentences into two piles. One pile for true statements, one pile for false statements. It didn't understand meaning. It followed rules. If the content of a sentence matched the world, it went in the true pile. If not, it went in the false pile. Now Cale fed the machine one sentence. This statement is false. What does the machine do? It tries to read it. It sees that the sentence is talking about itself, so it looks at the content. It sees that if the sentence is true, then it must be false. That means it doesn't belong in the true pile, so it puts it in the false pile. But now the sentence has said something that matches the world. It said it was false, and the machine agreed. That makes the sentence true, but it just placed it in the false pile. The machine tries again, it moves it to the true pile. Now the sentence is true, but it says it is false. That can't happen. The machine stalls. Its rules don't allow for this kind of loop. It was built to deal with simple truth values, not statements that collapse under their own meaning. Cale liked that image, a machine locked in a loop. doing everything right and still getting nowhere. He looked deeper into the history of the problem. Philosophers had known about it for over 2,000 years. The liar paradox appeared in ancient Greece. A man named Epimenides from Crete supposedly said, "All Cretans are liars. If he was telling the truth, then he must be lying, since he is a Cretan. If he was lying, then maybe not all Cretans are liars, which would make his statement false, but then perhaps true again." Kayla saw that the core of the paradox didn't change over time. It came back to the same point. A sentence that talks about itself in a way that makes assigning a truth value impossible. It doesn't just resist being understood, it breaks the tool we use to understand it. To test this more, Cal made another version. Sentence A, sentence B is false. Sentence B, sentence A is true. He thought maybe separating the reference would help, but it didn't. If sentence A is true, then sentence B is false. But sentence B says that sentence A is true. So if B is false, then A is not true. That creates the same loop. Kale saw that the problem wasn't self-reference alone. It was a certain kind of self-reference, one that involved negation. A sentence saying something about itself that denies what it says. Not just a loop, but a contradiction loop. A loop with no stable point. He explored formal logic systems to see how they handled this. In classical logic, every statement must be either true or false. There is no third option. But the liar paradox breaks that rule. It's not just unclear, it actively prevents either label from being applied. That's what made it dangerous. Some logicians tried to fix it. They introduced systems that allowed for a third truth value, something like undefined or indeterminate. In those systems, a sentence like, "This statement is false," doesn't get a true or false label. It gets marked as neither. That approach works for some cases, but it changes the foundation of logic. It says that not all statements can be judged by true or false. That unsettled Kale. He kept writing variations. "This sentence is not provable. This sentence will never be read aloud. This sentence is a lie." Each one played with the same mechanic. Self-reference, denial, circular meaning. Kale found that computers, when programmed with basic logic, also failed to handle these statements. They either entered infinite loops or returned errors. In software, an error like this could crash a system. In human thinking, it could crash a conversation. He remembered a moment in a philosophy class when a professor used the paradox to challenge a student's belief in absolute truth. If every sentence is either true or false, what do we do with this one? The student had no answer. Kale saw that the liar paradox wasn't just a curiosity. It forced people to face the limits of their frameworks. It showed that even basic language could defeat the rules we depend on. That wasn't a flaw. It was a feature. A reminder that some boundaries don't bend. They collapse. In his notebook, Kale wrote one more sentence. "This sentence cannot be trusted." He looked at it for a long time. He didn't try to solve it, he just let it sit. Jonah spent most of his time alone in the university library's archives. He was a graduate student studying logic and the foundations of mathematics. The room smelled like paper and dust, and the shelves held books that hadn't been touched in years. Jonah liked it that way. It gave him space to think without interruption. One afternoon, he came across a reference in an old index card that puzzled him. It listed a catalog titled "The Complete Index of All Books That Do Not Include Themselves." There was no other information, no author, no publication year, just that strange title. He couldn't find a copy in the archives. He asked the librarian, who said the title sounded like a joke or a puzzle. But Jonah was interested. He liked puzzles. He wrote the title down in his notebook and circled it. He went home that evening and kept thinking about it. The catalog listed books that do not list themselves. That part made sense. Some books refer to themselves. A dictionary might define dictionary within itself. A catalog of books might include its own title, especially if it's comprehensive. So a list of books that don't include themselves would simply skip any self-referencing books. But then the next question came. Does the catalog list itself? Jonah paused. If it includes itself, then it violates its own rule, because it claims to only list books that do not include themselves. So by including itself, it becomes a book that includes itself, which it says it doesn't. But if it does not include itself, then by definition, it qualifies to be in the catalog, which means it should be listed. But if it gets listed, then it includes itself again. and the cycle restarts. This wasn't just a clever word game. Jonah realized it was the same problem at the heart of some of the biggest ideas in logic. The structure of the puzzle mirrored a type of self-reference that breaks systems from the inside, a loop with no clear escape. He remembered a class discussion about Bertrand Russell. In the early 20th century, Russell faced a similar problem when working on set theory. He asked about the set of all sets that do not contain themselves. Does that set contain itself? If it does, then it doesn't. And if it doesn't, then it must. That simple question exposed deep cracks in the foundation of mathematical logic. It wasn't just theory, it stopped a whole system from working. Jonah opened a clean page in his notebook and wrote the word catalog at the top. Then underneath, he listed several imaginary books. Book 1, The Birds of Northern England. It does not list itself. Safe. Book 2, A History of Self-Referencing Books. Possibly lists itself. Maybe not safe. Book 3, Famous Catalogs of the 20th Century. No idea. He added a final entry, the complete index of all books that do not include themselves. And then next to it, he wrote a question mark. He stared at the question mark for a while. He thought about computer code. He'd written programs that called themselves in loops using a method called recursion. Sometimes, recursion worked. A function might call itself to process a tree of data, breaking it down into smaller parts. But other times it didn't. A careless recursive call with no end condition led to a stack overflow. The program crashed because it fell into an infinite loop. That's what this catalog was doing. It defined itself by what it was not, and the definition turned in on itself. No endpoint, just a spiral. He started wondering where else this happened. He remembered a painting he saw as a child, one that showed a hand drawing another hand, which in turn drew the first hand. He didn't understand it then, but it stuck with him. Now he saw it for what it was, a closed loop of self-reference. Another example came to mind, the barber paradox. A barber shaves everyone in town who does not shave themselves. So who shaves the barber? If he shaves himself, then he shouldn't, because he only shaves those who don't. If he doesn't shave himself, then he must, because that's his job. It sounded absurd, but it showed a real logical issue. Self-reference isn't always a problem. A book might refer to itself on purpose. A song might mention that it is a song. But when a system uses self-reference to define what is not allowed, it creates tension, especially when the definition reaches back on itself. Jonah imagined building the catalog himself. He pictured a digital database. Every book had a tag, either includes itself or does not include itself. Easy enough for most books, but what about the catalog itself? If he left it out, the catalog qualified for inclusion, so he added it. Then the catalog included itself, which meant it no longer qualified, so he removed it. But then it qualified again. The toggle never ended. His program would crash. In mathematical logic, Jonah knew this type of problem was important. It wasn't just a curiosity. It had consequences. When Kurt Gödel came along in the 1930s, he used self-reference to prove something shocking. He showed that any consistent mathematical system that was complex enough to describe basic arithmetic would contain true statements that couldn't be proven within the system itself. He did it by building a self-referential statement, one that said, in effect, this statement cannot be proven. It was like the catalog. If it could be proven, it would be false. If it couldn't be proven, then it was true, but unprovable. That result shook the world of mathematics. It meant that no matter how hard we tried, we could never build a system that was both complete and consistent. There would always be gaps, always be truths that slipped through. Jonah copied that result into his notes. He wrote, "Some truths live outside the system." The catalog was a simple version of that same idea. It made the problem visible to the eye. A book that listed books that didn't list themselves became a doorway into a deeper issue. The issue wasn't the book, it was the definition. Jonah got up from his desk and walked to the whiteboard. He wrote one sentence in the center. This sentence is false. He looked at it for a while. Then he added a second line. If the sentence above is true, then it is false. Then a third. If the sentence above is false, then it is true. It all looked silly at first, like wordplay, but it reflected the same twist. Self-reference, when left unchecked, could tangle even the clearest logic. It could make systems collapse, It could lead to truths that could not be caught by proof. Jonah returned to his desk and wrote a final note to himself. The catalog didn't fail because it was flawed. It failed because it was complete. It applied its rule to everything, including itself. And in doing so, it found the edge of what rules could do. He put the notebook away. The catalog didn't need to exist in the archive. It existed in the question. And that was enough. Elias worked in a small office that overlooked the city's central park. He was a philosophy professor at the local university, known for asking quiet questions that made people uncomfortable. He rarely raised his voice during lectures. He preferred slow, clear steps. His students often said his classes felt more like puzzles than lessons. One afternoon, during his seminar on metaphysics, a student raised a hand and asked a familiar question. Can God create a rock so heavy that even he can't lift it? The class chuckled. Most had heard the question before. It sounded clever, maybe even silly. But Elias didn't smile. He closed his book, stood still, and repeated the question aloud. The room quieted. Elias began walking slowly from one end of the room to the other. He explained that the question wasn't really about rocks or strength. It was about the concept of power itself and what it meant to be all-powerful. He said, imagine a being that can do anything. That's how many people describe an all-powerful God. The word used in philosophy is omnipotent. It means unlimited power, no boundaries, no limits. But then the question asks, what happens when power turns on itself? If God can do anything, then surely he can create a rock of any size or weight. That includes a rock so heavy that no being could lift it. But if he creates that rock and then cannot lift it, doesn't that mean there's something he can't do? That he lacks the power to lift it? On the other hand, if he cannot create the rock in the first place, then again, there's something he cannot do. In either case, something appears outside the reach of his power. That's the loop. The question doesn't have a clear answer because it's built from a contradiction. Elias gave another example. He asked the class to think of a square circle, not a picture or an illusion, but an actual shape that is both perfectly square and perfectly circular at the same time. The room was quiet again. The minds in the room turned over the idea, trying to make it fit. But it couldn't. The definitions clashed. A square has 4 straight sides and sharp corners. A circle has 1 smooth, unbroken curve. To be one is to not be the other. That was the key. Elias explained that some things are not just hard to do. They are logically impossible. They don't describe real tasks. They describe contradictions. A square circle isn't something that's difficult. It's something that doesn't make sense. So when we ask whether an all-powerful being can make a rock too heavy for itself to lift, we're doing the same thing. We're not describing a challenge or a task. We're describing a contradiction. The question forces us to imagine a situation that violates the very definition of omnipotence. He said the problem isn't with God or power. The problem is in the way the question is built. Elias often told his students that definitions matter. You can't stretch words until they break, then blame the meaning for falling apart. If we define omnipotence as the power to do anything that is logically possible, then the paradox disappears. Creating a rock that God cannot lift becomes like creating a square circle. It's not a sign of weakness to say that a being cannot do what cannot be done in principle. He wrote a sentence on the board. Omnipotence does not include the power to make nonsense true. Then he stepped back and asked the class to imagine a programmer writing code for a simulation. Inside the simulation, the characters follow the rules the programmer sets. The programmer can change the gravity, the speed of light, even the flow of time. But can the programmer make the code behave in a way that breaks the logic of the system itself? Could they write a function that says something both is and is not true at the same time? They could type it, but the system would crash. The rules wouldn't hold. The contradiction would break the structure. He said that even in imagined worlds, logic holds firm. Power works within that logic, not outside it. You can stretch it, but you can't step beyond it. Later that evening, Elias sat alone at a small cafe downtown. He had a notebook in front of him and a black pen. He didn't write anything. He just let the earlier conversation sit in his mind. The question came back again. Could God create a rock so heavy that even he couldn't lift it? He thought of how people use power in everyday life. Parents make rules for children, then sometimes break those rules. Governments create laws and change them later. These acts might look like pure power, but they aren't. They happen within systems, with trade-offs and limits. Power in that sense is always relative. The idea of a being with no limits feels different. It pushes against how humans experience power. People are used to tools and machines, lifting and moving, building and breaking. But power in the abstract isn't about muscles or mass. It's about scope. If you define a being as capable of all logically coherent actions, then you have to accept that some combinations of words don't describe coherent actions at all. The next morning, Elias returned to the classroom with a new example. He asked students to imagine a sentence. This sentence is false. It sounds simple, but if it's true, then it must be false. If it's false, then it must be true. It loops endlessly. It doesn't mean anything. It's a contradiction in the shape of a sentence. Then he compared that sentence to the rock question. Both rely on a form of self-reference. They turn back on themselves and create a problem that can't be solved from within. Just like the sentence collapses under its own logic, the rock question breaks down because of how it's framed. He drew a small box on the whiteboard and labeled it the possible. Everything inside followed the rules of logic. Arithmetic worked, shapes made sense, time had direction. He said omnipotence applied inside that box. Outside of it, nothing could exist, not even the idea of power. The question wasn't about limits in the ordinary sense. It was about recognizing where meaning ends. Asking whether an all-powerful being can do the logically impossible is like asking whether red tastes like Tuesday. The sentence forms. The words are clear. But the meaning isn't there. Elias left the classroom with his notebook under one arm. He didn't have final answers. That wasn't the goal. The goal was to keep the thinking honest, clean, direct, and free from illusion. The power of a question isn't always in what it answers. Sometimes it's in how it sharpens the edge between what can be known and what simply can't be said. Clara worked in a library that stretched beyond her understanding. It had no front door, no roof, and no visible end. The walls were bookshelves, and the bookshelves formed hexagonal rooms. Each room opened into another, and then another, as far as she could see. Every room looked the same. Every shelf was full. Each book was the same size. Hundreds of pages, neatly bound, filled with symbols, letters, and punctuation. Some made sense. Most did not. The rules of this library were simple. It contained every possible book that could be written using a fixed set of characters. The characters included every letter, every number, every piece of punctuation. Each book was exactly 410 pages long, with 40 lines per page and 80 characters per line. That meant each book had a set number of possible arrangements. The total number of unique books was huge, but not infinite in the mathematical sense. Still, no person could read even a small fraction of them in a lifetime. The librarian who trained Clara told her that somewhere in this collection was a perfect copy of Shakespeare's complete works. Also, another book that was just like it, but with one comma missing. Another with the same words, but in reverse order. One with each word scrambled. One that began with Hamlet and ended with nonsense. There were books with no vowels. Books with pages full of the letter E, repeated endlessly. And there were books that made no sense at all, not even as noise. Some books repeated a random pattern of 5 characters over and over. Others looked almost meaningful, but failed on closer inspection. Clara didn't choose the job. She was born in the library. Her parents had found each other while searching for a book that made sense. Her mother believed that if she kept reading, she'd find the one true book, the one that explained why the library existed. Her father stopped believing that before Clara was born. He thought the books were random. Nothing in them mattered. He read because he had nothing else to do. He said the library was a prison made of hope. As a child, Clara asked how many books were in the library. Her mother gave her a number. It had millions of digits. It was a number so large that it could not be pictured, only named. Clara didn't care about the number. She cared about the idea. If every book that could exist already existed, then her own future was somewhere in the shelves. A book described her birth. Another predicted her death. Somewhere was a book that included the exact words she was thinking in that moment. When Clara was 12, she found a book written in a language she didn't know. It used familiar letters but followed rules she couldn't grasp. Still, it felt like it meant something. She copied it by hand, thinking it might be a code. She never broke the code. Years later, she found another book that looked similar. Page for page, it matched, except for one letter. That letter changed a single word. She realized then that for every book she read, thousands more differed by only a letter or two. The variations were endless. She met another librarian named Elias, who believed that the library was finite, not small, but bounded. Since the books were fixed in size and used a fixed alphabet, the number of possible combinations had an upper limit. That limit was a number larger than any person could count, but not infinite in the true sense. Clara accepted that, but the consequences were strange. If every possible book already existed, then creativity changed meaning. Writers didn't invent new stories. They uncovered them. Somewhere in the shelves was every story that ever could be told. The tragedy was that almost all of them were unreadable. Clara became obsessed with finding meaning. Not perfect books, but readable ones. She created a tagging system. She marked books that made some sense, sentences that held together for a paragraph or more. She built a small collection of these and read them over and over. One day she found a book that described her tagging system. It listed her room, her records, her name. It was written in the past tense. She threw the book into the dark and didn't sleep for days. The book returned 2 weeks later. Someone had placed it back in her pile. The cover was scratched. A page was torn. It was the same book. But now it was part of a loop. A book written about her, read by her, returned to her. Elias called these recursive texts. He said they were inevitable. If enough books existed, some would describe other books. Some would describe the act of reading. Some would describe the reader. Eventually, a book would describe itself. The library forced meaning into existence by sheer volume. Not by design, but by saturation. Clara and Elias walked the stacks together. They talked about the boundaries of knowledge. They tried to map the rooms. The layout had rules. Each room led to 6 others. There was no center, no beginning, no proof that the rooms formed a complete shape. Some thought the library was infinite. Others thought it curved back on itself. They found books that claimed the library was a test, books that said it was a punishment, books that described other libraries, each with a different logic. One book explained the rules of a world where no book could refer to another. Another book described a library made only of blank pages. Clara believed none of them. She came to think of the library as a mirror. It showed whatever a person brought into it. Those who searched for truth found fragments that confirmed their beliefs. Those who searched for nonsense drowned in gibberish. The same shelves held both. She once spent a year reading a single room's worth of books, over 300 books, each nearly 400 pages. She found 3 that formed a coherent story. The rest were filled with errors, patterns, and pages of random marks. When she finished, she threw away the story and kept the rest. The 3 good books could have been found in any room. But the gibberish showed her the texture of the library. She kept a journal, not because she believed it mattered, but because it helped her focus. She imagined someone finding her journal 100 years later. Maybe it would be a guide. Maybe it would be one of many journals that said the same thing. If every book existed, then her journal was already in the library before she wrote it. That idea made her pause. If her journal already existed somewhere on the shelves, what was the point of writing it? Elias told her the act of writing was the point. The library might already hold the book, but it had not yet passed through her hands. The difference was small, but important. She accepted that. Clara copied a paragraph from her journal and placed it in a random book. She left the book open on a shelf. She did not mark the shelf. She did not plan to find it again. She believed someone else would. Not by luck, but because the library demanded it. Given enough time, every page would be turned. Every word would be read. Every mistake would be repeated. That was the curse of the library, and also its promise. A man named Garrett was sitting in a prison cell when the warden came in with a strange announcement. The warden said Garrett would be executed by hanging on a weekday next week. It would happen on Monday, Tuesday, Wednesday, Thursday, or Friday. But the execution would be a surprise. He would not know the day ahead of time. When the guards came to take him, It would be unexpected. That was all the warden said before leaving. Garrett sat in silence for a long time. The statement didn't sit right with him. Something about it felt off. He started thinking through the logic of it. He needed to find the flaw or the catch. If he could prove the warden's claim wrong, maybe he could avoid the hanging altogether. He took out a piece of paper and began working backward. He started with Friday. Could the execution be on Friday? He thought about what would happen if he were still alive on Thursday night. If the execution hadn't happened by then, Friday would be the only day left. That meant he would know the execution was coming the next day. But the warden said the hanging would be a surprise. So it couldn't be on Friday. He crossed Friday off the list. Now he looked at Thursday. If the execution couldn't happen on Friday, then by Wednesday night, if it still hadn't happened, Thursday would be the only day left. That would make it predictable again. He would expect the execution on Thursday. That would also break the surprise condition. So Thursday couldn't be the day either. He crossed that off too. He continued this reasoning. If Thursday and Friday were ruled out, then Wednesday would also be expected by Tuesday night. He crossed out Wednesday, then Tuesday, then Monday. One by one, all the weekdays fell away. Garrett sat back. According to his logic, the execution couldn't happen at all. No day could satisfy both conditions. The hanging had to happen on a weekday, and it had to be unexpected. But as he just showed himself, no weekday could meet that requirement. He felt a strange kind of relief. The announcement had seemed threatening, but now it looked meaningless. The warden had made a statement that couldn't be true. The execution wouldn't happen. The logic proved it. On Monday, the guards didn't come. That made sense. Monday was the first day he had ruled out. On Tuesday, he woke up and looked at the ceiling, waiting. Still no guards. His confidence grew. Wednesday passed. No one came for him. He didn't feel fear anymore. He felt certain. He believed he had solved the problem. The threat was over. But on Thursday morning, just after sunrise, the cell door opened. 2 guards stepped in. One of them read out the order. The execution was scheduled for today. Garrett stared at them. For a second, he said nothing. He felt confused. He had ruled out Thursday. He had ruled out every day. But here the guards were, just as real as the floor beneath his feet. He was surprised. That was the paradox. The logic that had convinced him the execution couldn't happen was the same logic that made it possible for him to be surprised. His proof had erased the possibility from his mind. And because of that, Thursday became the perfect day for the hanging. It was the only day that would truly catch him off guard. The warden's original statement had seemed like a contradiction. It said 2 things: that Garrett would be executed on a weekday and that it would be unexpected. Garrett had shown that no weekday could meet both conditions. But the flaw wasn't in the statement. The flaw was in the assumption that logical deduction could rule out real events. The moment Garrett ruled out the execution, he made himself vulnerable to it. That was what made it unexpected. The prediction looped back on itself. By assuming that logic made the execution impossible, he set himself up for surprise. It wasn't just about days on a calendar. It was about the nature of knowledge and belief. This kind of problem appeared in other forms. Philosophers had studied it for years. It became known as the unexpected hanging paradox, though it also showed up as the surprise exam paradox. In that version, a teacher tells the class that there will be a surprise test next week. The students go through the same kind of reasoning. They eliminate each day until they believe no test can happen. But when it does, they are surprised. The logic eats itself. It breaks down because the act of prediction changes the outcome. Once you believe something can't happen, it becomes easier for it to happen without warning. Jonah, a philosophy student who read about Garrett's case years later, used it in his thesis. He tried to model the logic using formal notation, but it kept circling back to the same core problem: self-reference. When you make a prediction that includes your own knowledge about the prediction, you risk contradiction. Jonah tried to explain it to a class. He said, "Imagine you're told that something will happen next week, but you won't know which day. You begin eliminating days with reasoning, but the reasoning itself becomes part of the problem. If it convinces you that nothing will happen, then the event can still occur because you've ruled it out." That gap between belief and reality allows the surprise. One student raised a hand and asked, "Isn't that just a trick?" Jonah answered, "No, it's not a trick. It's a limit of logic when it tries to account for its own impact." He drew a timeline on the board, Monday through Friday. Then he showed how Garrett had eliminated each day, but then he circled Thursday. He said, "This is when it happened," because he didn't expect it anymore. The surprise became real because the logic had convinced him otherwise. The paradox revealed something important about the nature of knowledge. It showed that some systems break when they try to include themselves. When prediction becomes part of what's being predicted, strange things happen. Logic stops behaving the way we expect. That was what happened to Garrett. He wasn't wrong to use reason. But the situation he faced didn't allow logic to close the loop. It turned inward. It caught him in the gap between what he believed and what could still happen. On Thursday morning, as the guards led him down the hall, Garrett didn't resist. He walked quietly. He looked straight ahead. He didn't ask questions. He had believed he was safe. He had thought the execution couldn't happen, but it did. And in that moment, he understood what made it a surprise. Theo liked to build strange machines. He wasn't a scientist or an engineer, not in any formal sense. He worked maintenance at a small technical college and spent his evenings in the workshop, soldering old parts and rewiring whatever the students left behind. He preferred mechanical things to digital ones. Gears and switches made more sense to him than code. One night, after reading an article on paradoxes of infinity, Theo came across something called Thomson's lamp. It wasn't a real lamp. It was a thought experiment, an idea meant to stretch logic and make people uncomfortable. But Theo wasn't content with thought experiments. He wanted to see what would happen if you tried to build one. The rules were simple. You have a lamp. At time 0, it's off. After 1 minute, you turn it on. After another half minute, you turn it off. Then after a quarter minute, on again. Then 1/8 off, 1/16 on, and so on. Each switch takes half the time of the one before it. The total time adds up to 2 minutes. By the end of those 2 minutes, you flip the switch an infinite number of times. The question is, when the 2 minutes are up, is the lamp on or off? Theo set up a desk lamp in his garage. He attached it to a relay switch and controlled the timing with a small circuit board. He programmed the timer to cut each interval in half. He didn't actually expect it to reach infinity. No machine could. But he wanted to see what happened as it sped up, switching faster and faster. The lamp clicked on, off, off. The intervals shrank. Theo sat back and watched. After a while, the movement blurred. The circuit couldn't keep up. The physical parts hit their limits. But the idea stayed in his mind. He sketched it out on paper, mapping each flip on a timeline. The pattern was clear. The switch flipped after 1 minute, then at 1 minute and 30 seconds, then at 1 minute and 45 seconds, and so on. Every time it moved closer to the 2-minute mark, without ever quite reaching it. Theo looked at the math. The sum of all the time intervals was a convergent series. 1 plus 1/2 plus 1/4 plus 1/8 and on. The total approached 2, not approximately 2. Exactly 2. That was the strange part. An infinite number of intervals could still have a finite total. But what about the state of the lamp when the sequence was complete? He tried to think about it in physical terms. Suppose you had a perfect machine. Suppose time could be divided without limit. Suppose switches could move infinitely fast. At the 2-minute mark, the lamp would have changed state an infinite number of times. Every on followed by an off, every off followed by an on. No final switch could be labeled as the last one. There was no final change. So he asked himself, what was the state of the lamp at the exact 2-minute point? He tried to list the states. After the first minute, on. After the next half minute, off. Then on, then off. It kept alternating. The pattern never stopped. Every even-numbered switch turned it off. Every odd-numbered switch turned it on. But after infinity, is the count even or odd? That's where things broke down. You can't label infinity as odd or even. It's not a number you can step onto. It's a concept, a direction. So asking whether the final flip is number 1 million or number 1,000,001 doesn't work. There is no final flip. Theo realized that the paradox didn't just sit in the wiring or the timeline. It sat in the assumption that the process could have a well-defined end result. that after completing an infinite task, something definite had to be true. But the structure of the process didn't support that. It didn't favor either state. The lamp wasn't tending toward being on or being off. It kept switching endlessly without a final moment of decision. He thought about what it meant to complete something infinite. You can walk halfway across a room, then halfway again, then halfway again. You can repeat this forever, but in practice, you reach the other side, because the total distance is finite. That's the idea behind converging series. But with the lamp, the total time converges, while the action, the flipping, remains unsettled. The lamp doesn't converge to a state. It doesn't settle. The behavior doesn't have a limit. Theo wondered if you could model it in another way, maybe using a limit function. But no matter how he sliced the numbers, the outcome stayed undefined. The limit of the sequence of lamp states did not exist. It didn't approach one value. It bounced forever between on and off. That's not the same as flipping it once every second forever. That would just mean it's flipping constantly. But this process squeezes infinite flips into a finite space. That makes it different. He remembered an old logic class he once sat in on, where someone said that infinity isn't a number. It's a process. It describes unending growth or division. Trying to assign a definite result to an infinite process can lead to contradictions. Still, Theo kept going back to the lamp. Couldn't there be some trick? Maybe the mechanism had a flaw. Maybe a physical switch, no matter how fast, would naturally settle in one position. But he knew that was a distraction. The paradox wasn't about real machines. It was about what happens when you take ordinary rules and stretch them to their logical extreme. He wrote down a list of other examples. A bouncing ball that loses half its height each time. The total number of bounces could be infinite, but the ball would come to rest. That's different. In that case, the motion fades. The system has a limit, but the lamp never slows down. The flips don't shrink in energy or effect, just in time. That's the catch. Theo thought about writing a program to simulate the process visually. A screen that blinked black and white in faster and faster intervals. But he knew the screen would freeze or blur before reaching any real conclusion. That was the nature of the problem. He took the lamp apart. He unscrewed the bulb and coiled the wire. The parts were fine. Nothing had burned out. He placed them back in their box and sat for a while, the diagram still on the whiteboard. Thomson's lamp wasn't broken. It wasn't faulty logic. It was a reminder that infinite processes don't always yield neat answers. Some questions, when pushed past their limit, simply stay open. The lamp was not on. The lamp was not off. The lamp was undefined. Callum worked at a maritime museum on the coast. His job was to restore old ships. Some were dry docked for display. Others were set up in parts, like puzzles pulled apart to show their inner frames. The museum's centerpiece was a long wooden ship that once sailed in the 18th century. Visitors walked across a glass bridge suspended above it, looking down at the beams, the ribs, the deck, all carefully preserved, or at least carefully rebuilt. Callum had been there for 6 years. In that time, not a single piece of the ship remained untouched. The salt in the air had rotted parts of the hull. Wooden planks had cracked. Iron bolts had rusted. Each time something degraded, he or one of his coworkers replaced it, one beam at a time, one board at a time, never all at once. But slowly, over the years, the ship changed. Every part had been switched out. One afternoon, a school group visited. The guide was explaining how the ship had once crossed the Atlantic. One of the kids raised his hand and asked, "Is this still the real ship?" The guide laughed and looked up at Callum, who stood on the scaffolding nearby. "What do you think?" she asked. Callum didn't answer right away. The question wasn't new. It had been asked for over 2,000 years. The Greek philosopher Plutarch wrote about it. The idea was simple. If you replace each part of a ship, one at a time, until no original parts remain, is it still the same ship? Callum had thought about it before. He thought about it every time he pulled out an old nail and replaced it with a new one. Each piece of the ship had a lifespan. Wood rotted, metal corroded, paint faded. Maintenance meant swapping parts, not preserving them untouched. After the group left, he took out his notebook and started writing. He drew a diagram of the ship. He labeled every part that had been replaced since he arrived. Then he made a list of parts that had already been replaced before he was hired. The list went on for pages. When he finished, he realized that no part of the ship came from the original build. Everything had been restored, every plank, every nail. He paused. Was it still the same ship? He thought about how people might answer. Some would say yes. The ship kept its shape, it kept its name, it had been maintained with care. The continuity mattered more than the material. Others would say no. If none of the original parts remained, it was only a replica, a shadow of what it once was. He imagined another version. Suppose that every time he removed a part, he set it aside. One by one, he gathered all the discarded pieces in a warehouse. Then, he rebuilt the ship with those original parts. Would that ship be the real one? If so, then the museum's ship wasn't. But what if both were real? Or neither? The questions didn't have easy answers. Callum remembered replacing the ship's rudder the year before. It had snapped during a storm while on display outdoors. They couldn't save it. The new one was made from the same type of wood, cut to the same shape, treated the same way. To a visitor, it looked identical. But he remembered how it felt to remove the old one. It was heavy, worn, waterlogged. He could see the marks left by years at sea. That piece held history in its grain. He understood why people cared. Things gain meaning from their past. A ship that crossed the ocean 200 years ago feels different from one built yesterday, even if they look the same. Time gives weight to objects. So when all the parts are replaced, people wonder if the meaning remains. He walked to the far end of the museum, where another exhibit stood. It was a display of old clocks. One clock was built in the early 1900s, but only its outer casing was original. The gears, the hands, even the glass, each had been repaired or replaced. Yet the plaque called it an antique. No one questioned that. Callum wondered why ships felt different. Maybe because ships move through space, maybe because they have names and stories. He thought about a person. If someone broke a bone, doctors could put in a metal rod. If their tooth fell out, they could get an implant. If their heart failed, they might get a transplant. If they lost a limb, they could use a prosthetic. The person would still be the same person. Even if none of the original cells remained after a few decades, they stayed themselves. But when it came to a ship, people hesitated. He wrote another question in his notebook. Is identity based on material or on function? The ship still looked the same. It still sat in the same museum. It still told the same story. It was still treated as the same ship. Maybe that was enough. Maybe identity wasn't about what a thing was made of, but how we related to it. He thought about memory. People remembered the ship as one thing. They treated it with the respect earned by its voyages. That memory held it together, even if the materials changed. But he also knew someone could argue the opposite. If every part is different, then nothing remains of the ship that once sailed. The new version is just a copy, a high-quality replacement, but not the original. That view held weight too. Callum stood up and walked back to the ship. He ran his hand along the new railing. It was smooth and firm, sealed against moisture. He imagined the old version, cracked, splintered, fragile. The ship was stronger now, safer, better preserved. But was it the same? He wasn't sure. A few days later, he got a package in the mail. A friend had sent him a wooden box. Inside was a small model ship carved from driftwood. A note read, "Parts change, stories stay." He placed it on his desk. That night, he walked through the empty museum before locking up. The overhead lights reflected off the ship's polished surfaces. He looked at the hull, the masts, the rigging, all restored, all replaced, still standing, still recognized. Whether it was the same ship or not might not matter. People came to see it. They learned its story. They imagined what it had seen. And in that space, the question remained open. Not a flaw, but a feature. A way to understand how we think about identity, not as a fixed point, but as something carried forward, piece by piece. Talia stood in the clean, silent hallway of the time lab, looking at the door to the departure chamber. Inside was a device built to send people back in time. Not years or decades, centuries if needed. She had gone through the tests, the protocols, the risk assessments, but no one had done what she was planning to do. Talia was calm, focused. She wasn't doing this for exploration or curiosity. She had a reason. Her grandfather, Marcus, had done something years before she was born. Something that shaped the rest of her family's life. A decision that set everything off course. She never met him, but she knew his story. He had walked away when her father was still a child. No explanation, no return. That one act had echoed through generations. Her father never recovered. Her family drifted. She had read about paradoxes in her training. They were more than science fiction problems. They were structural conflicts. Logical breaks in time-based reasoning. The most famous one sat in her mind as she stepped into the machine, the grandfather paradox. It worked like this. Imagine a person travels back in time and kills their grandfather before the grandfather has children. Then the traveler's parent is never born, which means the traveler is never born, which means they never went back to commit the act, which means the grandfather lives, which means the parent is born, which means the traveler exists, which means they go back, which means the grandfather dies. The loop never settles. It flips endlessly. Talia wasn't interested in killing anyone. That was the thought experiment version. But she wanted to stop her grandfather from leaving. She believed that one act would change everything downstream. She had done the math. She had traced her family line. If she could stop him, convince him to stay, her father's childhood would be different, and maybe her own life would improve too. She activated the system. A short burst of heat passed through her chest. The lab dissolved in a quiet pulse of light. She opened her eyes and saw the world of 40 years ago. The air was warmer. The buildings were older. Her clothes looked out of place. She found Marcus easily. The records were accurate. He worked at a shipping yard on the coast. He had a routine. Talia watched for 2 days. Then she spoke to him. She didn't explain who she was. She told him only that someone cared about his choice, that leaving would cause damage he couldn't imagine. He looked at her carefully. Then he nodded. He said he had already changed his mind. He was staying. He just hadn't told anyone yet. Talia felt a tight pull in her chest. This should be enough. She returned to the place where the machine would pull her back. She stepped into the signal zone and waited, but nothing happened. She waited longer. Still nothing. Then she started walking. The city looked more familiar now. The buildings, the traffic, the people. She asked someone for the date. It was the year she had left, but something felt off. She found a public data center and searched her own name. Nothing. She searched her parents. Her father's name appeared, but not the way she remembered it. He had a different family, a different background. She kept reading and realized that Marcus had stayed. He never left. He raised his son. But that son didn't meet Talia's mother. They never married. Talia was never born. She stepped back from the screen. She was here in this world, but she wasn't supposed to be. Her actions had erased the very path that led to her creation. The paradox had closed around her. She had no clear origin now, no path through time that could explain her presence. She walked out into the street, unsure of what came next. The grandfather paradox wasn't just a puzzle. It described a real tension in cause and effect. If you change the past in a way that removes your reason for going back, then the change undoes itself. But if the change undoes itself, the original cause remains. That cause leads to the change again. The loop starts over. Some theories try to resolve the problem. One suggests that time resists paradox, that events in the past can't be changed in ways that affect the future inconsistently. If you try, something stops you. The gun jams. The person disappears. You lose your nerve. Time heals itself. Another theory suggests branching timelines. If you change the past, you don't overwrite your history. You create a new one. A parallel timeline branches off. You exist in both, but only one is your true origin. In that case, Talia hadn't erased herself. She had jumped into a world where she didn't belong. But the core of the paradox remained. Cause and effect broke down when the action canceled its own cause. It was like trying to remove the bottom step of a ladder while standing on it. The whole structure collapsed. Talia wandered for days. She had money from the lab, but no identity, no record, no past. She found work at a local research lab under a different name. She stayed quiet. She didn't try to contact the life that might have been hers. It didn't exist anymore. Each night she sat with the idea that her presence was an error, a leftover trace of a timeline that had wiped itself out. She started keeping notes. She wrote about the paradox. She detailed every step. She didn't know if she would ever return to her original world. She didn't know if it still existed. But she wrote because she wanted someone to understand. The grandfather paradox wasn't just a trick of logic. It was a warning. Changing the past doesn't only alter outcomes, it unravels the line that connects them. She wrote a phrase at the top of every page. If I stop myself from beginning, I never began. But if I never began, who stopped me? It echoed in her mind as she moved through each new day, a question without an answer, caught in a loop that had no clear start and no true end. Elena was a theoretical physicist working at a quiet research institute near the coast. Most of her work focused on closed time-like curves, hypothetical paths in space-time that allowed for time travel. It was still theory, still paper and equations, but her team had built models that showed these loops were not impossible, just difficult, just rare. She had always been curious about causality. What caused what came first? In her early days as a student, she asked questions most professors waved away. What if the cause and effect looped? What if something existed not because it was created, but because it was passed along? Those questions stuck with her. Now she had a way to test them, not with machines or devices, but with logic, thought experiments, controlled paradoxes. One night, Elena stayed late in the lab. Most of the lights were off. Only her desk lamp and the glow of her laptop lit the space. She wasn't working on equations. She was writing a story, a fictional story based on one of her favorite paradoxes. The story followed a woman named Iris who discovered a book on her desk one morning. The book was bound in red leather. It had no author's name on the cover. Inside, it detailed a theory of time travel unlike anything in current literature. Every chapter was clear. Every equation held. Iris checked the math. It was perfect. She couldn't explain where the book came from, but it was there, so she studied it. Years later, Iris became a physicist. She published papers. She advanced the theory found in the book. When she was older, and the world was different, she built a machine, not to go into the past herself, but to send the book back. She placed it in the time capsule and calibrated the machine to send it to her own younger self's lab. Then she activated it. The machine hummed. The book vanished. That's where the loop began. Elena paused and leaned back in her chair. She had heard people call this the bootstrap paradox, named after the idea of pulling oneself up by one's bootstraps. Something exists without a clear origin. It loops. It's self-contained. The book in her story had no outside author. Iris never wrote it. She only read it and sent it back. But someone must have written it. Or did they? She opened her notebook and wrote a single question. Where did the information come from? The paradox didn't involve contradiction in the usual sense. It wasn't like the grandfather paradox, where a person erases their own origin. In the self-creating loop, everything still happens. The events are consistent, the book appears, it is used, it is sent back, but there's no starting point. The loop has no anchor in time. It just exists. She thought of it in terms of logic gates. In electronics, some circuits feed their output back into their own input. These are called feedback loops. When designed carefully, they stabilize. They hold a state, but they don't explain how that state came to be. That's what made the paradox unsettling. If a time traveler gives a book to their younger self, who later grows up and passes that same book back, then who wrote it? The book exists, that's clear. The information is real. The math checks out. But the creation of the book, the act of writing it, never happens. It is not copied. It is not authored. It just loops. Elena searched for examples. She thought of songs. Imagine a musician who hears a tune played by someone from the future. They memorize it, and when the time comes, they perform it. That performance is then recorded and sent back in time, where the younger musician first hears it. The loop completes, but the tune was never composed in the normal way. It was passed, preserved. The creative act is absent. She wrote another note. The paradox is not about failure. It is about the absence of origin. The implications were large, not just for storytelling, but for physics. If time travel were possible, then information could appear in the universe without a source. A design, an idea, a formula. It could exist purely because it was preserved and transmitted. No author needed. The laws of causality would still hold, locally. Each person still acted with intention. Each step followed from the one before. But the chain formed a circle. She looked at her notes and tried to model it. Let event A be the receipt of the book. Let event B be the use of the book's contents to create a time machine. Let event C be the act of sending the book back in time. A causes B causes C causes A. No outside cause, no entry point, just the loop. She ran through objections in her head. Maybe the book degraded slightly each time. Maybe the loop couldn't last forever. Maybe entropy would intervene. That was possible. But in theory, the loop could remain intact. Quantum information could stay preserved. The paradox didn't require infinite cycles, only one. And then she wondered something deeper. If a universe allowed for this kind of loop, could the entire universe be self-creating? She remembered reading speculative physics papers that explored the idea. A universe that created itself by sending quantum information back in time. A kind of self-consistent loop on a cosmic scale. It sounded strange, but no stranger than a book without an author. She thought again of Iris and the book. She imagined the younger Iris opening the book and reading the words, understanding them, trusting them, never knowing where they came from, but building her life around them. Then, decades later, becoming the person who made sure those words reached her younger self. The identity of the author becomes meaningless. The contents exist. They have no origin, but they function. They change lives. They shape events. In mathematics, a system without foundations usually collapses. You need axioms. You need starting points. But in physical systems, maybe a loop could hold itself in place. Elena closed her laptop. The story felt finished, even without an ending. She didn't need to explain who wrote the book. That was the point. The paradox wasn't about confusion. It was about limits. The limit of causality. The edge where explanation stops. She turned off the desk lamp. The room darkened. In the hallway, her reflection followed her in the glass. She wondered, briefly, if someday someone might hand her a paper with her own name on it. One she hadn't written, not yet. But one she might. If that happened, would she write it down, or just pass it along? She didn't know, but she knew she would keep asking the question. Who wrote the book? And maybe that was enough. Nathan stood at the edge of the chalkboard in a dim lecture hall, drawing a circle to represent a black hole. He had been working on his thesis for 3 years, and it all pointed to this, an object so dense that no light could escape. He knew the equations, he knew the definitions, but he also knew there was a problem in the middle of it all, a place where the math broke, a place called the singularity. He stepped back and stared at the center of the circle. He wrote 2 words beneath it, infinite density. Then he paused. That was the term used in most textbooks. It showed up in lectures, in documentaries, even in science fiction. But it didn't feel solid. It felt like a placeholder, a way of saying, we don't know what happens here. The idea came from general relativity. Einstein's theory said that gravity wasn't just a force, it was the bending of space and time caused by mass. A planet bent space a little, a star bent it more. But a black hole bent it so much that the curvature became extreme. At the center of that curve, the equations said the density became infinite. All the mass of a star collapsed into a point with 0 volume. Nathan ran through the math again. Density is mass divided by volume. If mass stays constant and volume drops to 0, density goes to infinity. But in real life, infinity isn't a number, it's a concept. It means something grows without bound. In physics, that's a red flag. When infinity shows up in an equation, it often means the model has hit its limit. The math doesn't match reality anymore. He thought about what that meant for black holes. If the singularity had truly infinite density, then the gravitational pull at that point would also be infinite. That suggested space would be torn completely. Time would stop. Every known law of physics would collapse. But the equations didn't stop at that point. They just kept going. He remembered a lecture where his professor explained that singularities are where general relativity breaks down. The theory can't describe what happens inside that point. It predicts its own failure. Nathan found that both troubling and fascinating. Physics had a model that predicted black holes, but at the heart of those objects, the model stopped working. He wrote another term on the board, Planck length. That was the smallest meaningful unit of space, according to quantum theory, around 10 to the power of minus 35 meters. Smaller than that, and space itself stopped making sense. Distances lost meaning, quantum fluctuations dominated. The singularity of a black hole was smaller than that, at least in the math. But quantum mechanics didn't agree. This is where the two big theories, general relativity and quantum mechanics, refused to meet. One described large-scale gravity. The other described particles and forces at the smallest scales. But they didn't merge. Each had limits, and the singularity sat right at the intersection of those limits. Some physicists believed that infinite density was a sign that general relativity needed help, that at scales close to the singularity, quantum effects would take over. They believed a full theory of quantum gravity would smooth out the singularity. Instead of a point of infinite density, the center of a black hole might become a region of extreme but finite density, where space and time were quantized. But no one had that theory yet. Nathan reviewed attempts to patch the problem. The idea of a quantum bounce had been proposed. Instead of collapsing forever into a point, matter might bounce back, forming a new expanding universe inside the black hole. Others suggested that singularities never actually form. They believed that some unknown pressure stopped the collapse just before the density became infinite. These were just models. None had been proven. He turned to the concept of event horizons. That was the boundary around a black hole, the point of no return. Nothing inside it could escape, not even light. From the outside, it didn't matter what happened at the singularity. You couldn't see it, you couldn't touch it, you couldn't measure it. So some physicists treated it like a theoretical boundary. They didn't worry about the singularity itself because its effects couldn't leave the black hole. But Nathan wasn't satisfied with that. He believed something real had to exist inside, even if no one could see it directly. The singularity wasn't just a hole in space, it was a hole in our understanding. Leaving it unexplained felt like skipping the hardest part of the question. He ran through another scenario. Imagine a star much more massive than the sun. When it runs out of fuel, gravity pulls it inward. The outer layers collapse. The core crushes under its own weight. No known force is strong enough to stop it. The matter becomes denser. Neutrons are pushed together, then quarks, then whatever comes next. At some point, if the collapse continues, all the mass falls into a point. That's where general relativity says the density becomes infinite. But infinite density also means zero volume. And zero volume means no space, no structure, no boundary. Just a point, with mass and gravity, but no size. That doesn't line up with any physical object we know. He thought about analogies. On a map, the North Pole is a point where lines of longitude meet. It's not a place with area, it's a limit of the coordinate system. The singularity might be similar. It might not be a physical point inside space. It might be the edge of space itself, where space stops behaving like space. Some physicists compared it to the Big Bang. That singularity was also a point where density was infinite. But instead of collapsing inward, it expanded outward. The math worked in reverse, but the limits were the same. In both cases, time and space reached a point where the known laws broke. That meant singularities were not just features of black holes. They were features of the universe. Nathan went back to the chalkboard and erased the phrase infinite density. He replaced it with breakdown of known physics. That felt more honest, more accurate. The term infinite density was a signal. It told you that the math had hit a wall. He remembered something else. When physicists study real black holes like the ones detected by gravitational waves, they don't measure what happens at the singularity. They measure how black holes affect things around them. Their mass, their spin, their electric charge. All of these things are observable. But the singularity itself stays hidden. He wrote those three terms on the board: mass, spin, charge. Those were the only things a black hole showed to the outside world. They formed what physicists called the no-hair theorem. It didn't matter what the black hole was made of. Once it collapsed, only those three traits remained. That added to the mystery. 100 different stars could collapse into black holes, each made of different materials, different histories, different chemical makeup. But in the end, each one became a black hole with mass, spin, and charge. Nothing else left a trace. The singularity wiped it clean. Nathan leaned against the desk. He had been chasing the idea of infinite density for a long time, but now he saw it differently. It wasn't a final answer. It was a question wearing the mask of an answer. A warning label in the middle of the theory. It didn't tell you what was there. It told you that something was missing. Elliot worked night shifts at an observatory just outside the city. His job wasn't glamorous. He logged data from telescopes, adjusted software, and sometimes helped visiting researchers set up their experiments. He liked the quiet. The long hours gave him time to read. He wasn't a physicist, not officially, but he'd taken courses in cosmology and had shelves full of books about space. He liked ideas that pushed the limits of what we could imagine, and one idea had been bothering him for months. He read about the infinite universe hypothesis on a slow night in December. The observatory's telescope was down for maintenance, so he stayed in the control room, flipping through a physics journal. The article was short, only a few paragraphs, but the idea stayed with him. If the universe is infinite, then space goes on forever. If it goes on forever, then all possible arrangements of matter must occur, eventually. That includes planets, stars, galaxies, and people. Somewhere, in a region of space so far away that no light from it could ever reach us, there could be another version of Earth. On that Earth, there might be someone exactly like Elliot, sitting at a terminal, drinking the same brand of instant coffee, reading the same article, thinking the same thought. It wouldn't just be someone similar, it would be him. His copy. Atom for atom, memory for memory. It sounded impossible, but the logic didn't rely on strange physics. It was based on simple probability and scale. Matter can only arrange itself in so many ways. The observable universe contains a finite number of particles, roughly 10 to the power of 80. Even accounting for all the possible combinations, the number is still finite. But if space is infinite, and if those finite combinations are repeated in infinite space, then duplicates are not just possible, they're inevitable. Elliot closed the journal and looked out the window. He couldn't see much, just the outline of trees and the orange glow of a distant highway. But somewhere beyond the horizon, past the edge of the galaxy, past clusters of galaxies, beyond the cosmic microwave background, the same story might be unfolding. It was hard to grasp. Not because the numbers were difficult, but because the idea refused to stay abstract. He stood and walked to the whiteboard. He drew a small circle to represent a region of space. Inside, he wrote Earth. Then he drew another far away and wrote copy of Earth. Then another and another. Each one identical, spaced far apart. He didn't bother with scale. That part didn't matter. The point was that in an infinite space, every possibility played out somewhere. He remembered something from probability class. If you flip a coin forever, you'll eventually get every possible sequence. That means there will be a stretch of flips that matches any sequence you choose. 10 heads in a row, 100 heads, or any pattern, no matter how long. The longer the pattern, the rarer it is. But given infinite flips, it will happen. Not just once, infinitely often. He applied the same logic to matter. There are only so many ways to arrange atoms into a human being. That number is huge, but it isn't infinite. If space is infinite and filled with matter, then the arrangements must repeat. And that means someone, somewhere, has already lived this exact night, in this exact observatory, thinking these exact thoughts. The idea wasn't new. Physicists had written about it. Philosophers too. It had a name: cosmic duplication or infinite recurrence, depending on the context. It didn't require alternate dimensions or branching timelines, just an endless stretch of space and time governed by known physical laws. Elliot pulled up a simulation on the observatory's computer. It showed a zoomed-out map of galaxy clusters. The universe looked like a web with strands connecting bright nodes. That pattern stretched as far as the model could simulate. Beyond that, the map faded into black. But the theory said there was more. Much more. No edge, no boundary, just more of the same. He imagined flying a ship in a straight line forever. After billions of light years, he'd pass regions of space unlike anything we'd ever seen. But eventually, by sheer statistical chance, he'd arrive at a region identical to home. Not just similar, identical. Same constellations, same planets, same people. There might be a version of himself just 500 billion light years away. Another version twice that distance. Another 1 trillion light years out. The distances were incomprehensible, but the principle held. He wondered if those versions of himself knew about him, or if they were thinking the same thing right now. Maybe some had already figured it out. Maybe others never would. He sat back down and scribbled notes. The problem wasn't just that these copies might exist. It was what their existence meant. If someone else lived his life in every detail, did that make his choices less meaningful? If every version of him made every possible decision, was free will just an illusion created by randomness? He didn't like those questions. They felt too large. He reminded himself that infinity didn't cancel out experience. Just because every possibility happens somewhere doesn't mean it stops mattering here. This version of him was the one thinking, feeling, choosing. The others were abstractions, real, maybe, but unreachable. The universe had a horizon, not a physical edge, but a limit to what we could see. Beyond that, space might go on forever, but light hadn't had time to reach us from there. That region, the observable universe, was like a bubble. Inside, there was only one Elliot. Outside, the duplicates waited, unknowable. He thought about language. People said infinite all the time, but rarely meant it. They used it in poetry or exaggeration. But in physics, infinite meant something cold and precise. No end, no limit, no exception. He opened a file and began typing. He wanted to record his thoughts before the feeling faded. He described the night, the journal, the idea of copies. He tried to write plainly, not as a scientist, but as someone trying to understand. He wrote that if space was infinite, then matter must repeat. And if matter repeats, then people repeat. Somewhere, someone else had written these same words, in this same file, in this same moment. The only difference was distance. Not time, not choice, just distance too vast to ever bridge. He paused before saving the file. Then he named it Elliot 1. Not because he believed he was the first, but because this version of him needed a name. The wind outside picked up, the observatory creaked, the stars overhead stayed fixed. He looked up at the ceiling and tried to imagine all the other ceilings above all the other versions of himself. Then he looked back at the screen and kept typing. Noah worked the late shift at the observatory on the edge of town. He liked the quiet. The building sat high on a ridge, far from streetlights and traffic. The sky above stretched out in every direction. On clear nights, it seemed endless. That view is what pulled him into astronomy. He liked looking into deep space, not just through the telescope, but through questions that had no easy answers. One night, while recalibrating the main telescope, he looked up without any tools. The stars were visible, scattered across the black sky. It was peaceful, but the more he stared, the more he felt something odd. The sky was mostly empty. He saw points of light, but between them was darkness. A lot of it. He remembered a question from his first year of college. His professor had written it on the board without explanation. Why is the night sky dark? At the time, it seemed like a trick. Of course it's dark. The sun isn't shining on that part of Earth. That's what night is. The answer felt obvious, but the professor pushed further. If the universe is infinite, filled evenly with stars in every direction, then every line of sight should end on the surface of a star. No matter where you looked, you should see light. The night sky should be as bright as the surface of the sun. That didn't happen. The sky was dark, almost completely black. That was the paradox. Noah went back inside and pulled an old book from the shelf. He flipped to a section on historical cosmology. The problem had a name, Olbers Paradox. In the early 19th century, a German astronomer named Heinrich Olbers asked the same question. If the universe was eternal and filled with stars, why wasn't the night sky glowing? At first, people suggested that dust between the stars might block the light. But that didn't work. If the universe had existed forever, then over time, the dust would absorb the starlight, heat up, and start to glow itself. Eventually, the sky would still shine just as brightly. Others said maybe the stars were just too far. Maybe their light hadn't reached us yet. But in an infinite, eternal universe, distance doesn't help. Light from faraway stars would have had endless time to arrive. So again, the sky should be bright. The logic was simple. If space goes on forever and stars are spread throughout it, then light should hit Earth from every direction. There should be no gaps. Darkness should be impossible. But we see the opposite. We see darkness. Noah stared at the dark ceiling above the telescope bay. He pictured the stars he couldn't see, the ones blocked by the dome or hidden behind the Earth. There were billions, maybe more. So why was there still so much space between them? Modern physics had answers that Olbers didn't. First, the universe isn't eternal. It has an age, roughly 13.8 billion years. That means we can only see light that's had time to reach us since the beginning. Anything farther away than that distance hasn't had time to send its light here. The edge of the visible universe is a hard limit. We call it the observable universe for that reason. Second, the universe isn't static, it's expanding. The space between galaxies stretches. That expansion changes the light from distant stars and galaxies. It stretches the light waves, shifting them toward the red end of the spectrum. The farther the light travels, the more it shifts. Some light from the earliest galaxies has stretched so much that it's no longer visible to the eye. It's in the infrared or microwave range. Instruments can detect it, but we can't. That expansion also means galaxies move away from each other. The farther away a galaxy is, the faster it recedes. That speed lowers the energy of the light that reaches us. So even when we do see distant galaxies, they look dimmer than they would in a static universe. Noah thought about how this tied into the cosmic microwave background. That faint glow is the leftover light from the early universe, now stretched into microwaves. It's uniform in all directions, but invisible to the eye. If we could see in microwave wavelengths, the sky would never be dark. It would glow with ancient light. The third reason the night sky is dark involves the lives of stars. Stars aren't eternal. They have lifespans. Some burn for billions of years. Others explode after a few million. That means stars haven't always existed, and they won't always exist. The sky is not filled with infinite, eternal stars. It's filled with stars that were born, live, and die. The finite age of stars limits the amount of light in the sky. Combined with the finite age of the universe and the stretching of light over time, these three factors explain the darkness. Still, the paradox holds weight. On paper, infinite space filled with infinite stars should give infinite light. But we don't live in that universe. We live in one that began at a point in time, one that expands, one that changes. Noah used to think of the night sky as empty. Now he saw it differently. The darkness wasn't emptiness, it was information. Each dark patch told him something about the structure of the cosmos, beginning about its limits. He wrote a note for his students. He was scheduled to teach a class next week. The note read, "If the night sky were bright in every direction, we'd have no reason to question the structure of the universe. The darkness is the clue." He wanted them to see what he saw. The black between the stars wasn't a failure of imagination. It was a sign of how the universe works. Without it, we'd still believe in an eternal, unchanging cosmos. He thought about Olbers. The man saw the same sky and asked a question no one had asked seriously before. Why, in a universe filled with stars, do we see so much dark? That question led to deeper ones, not about starlight, but about time, expansion, and the shape of space itself. Noah closed the book and walked back outside. The sky was still dark, still scattered with light. He knew now that the blackness said more than the stars ever could. Eli was a physicist who taught at a small college in the mountains. He had always been drawn to the edges of science, where theory met uncertainty. His lectures stayed close to the basics, but in private, he explored the stranger parts of quantum mechanics. One of those ideas never stopped bothering him. It was called quantum immortality. He first read about it during graduate school. It came from the many worlds interpretation of quantum mechanics. The theory said that every time a quantum event could go more than one way, reality splits. One version of the universe goes left, another goes right. The versions don't cancel each other out. They all continue side by side in different branches of reality. That alone was strange. But quantum immortality pushed it further. It asked what would happen if your life depended on a quantum event, one that had a chance of killing you. According to the theory, in some branches, you die. In others, you survive. The key question was this: from your own point of view, which version do you experience? The theory answered, you always find yourself in the branch where you survive. Eli couldn't ignore that answer. If it were true, it meant you would never experience your own death. Not because death didn't happen, but because in every moment that risked death, somewhere in the multiverse, there would be a version of you that made it through. Over time, this would mean something extreme. In your own eyes, you would live forever. You would never be gone. Your friends, your family, your world might fade, but you would continue. The idea sounded absurd, but it followed directly from the logic of the theory. Quantum mechanics did not forbid it. It simply suggested that survival was always possible, and that consciousness followed the path where it continued. Eli tried to ignore it for a while. He told himself it was a thought experiment, not something real. Then he met a colleague named Mira who had worked on similar ideas. They would talk late into the night, sitting in the lab, surrounded by old instruments and empty coffee cups. One evening, Mira asked a question that Eli had been avoiding. She said, "If you believe in quantum immortality, what does that do to your choices? What does it do to your sense of risk?" Eli didn't have a clear answer. He had always believed that actions mattered, that decisions had weight, but the theory undercut that. If every outcome happened somewhere, then did it matter what he chose? If death was always avoided in one branch, did risk still carry meaning? He tried to break it down. He imagined a machine. Inside the machine, a particle decayed or didn't decay. If it decayed, the subject lived. If it didn't, the subject died. The chance was exactly 50%. In one branch, the person died. In the other, they didn't. Now imagine repeating the experiment many times. Every time the person wakes up, surprised to be alive, they see a growing string of impossibly lucky escapes. From the outside, observers would stop seeing them. In the shared world, they would have died, but from their own view, they kept going. This was what disturbed Eli most. The experience of the person didn't end. The world around them could shift, grow stranger, fall apart. But consciousness followed the line where it stayed awake. He started tracking coincidences. Times he had narrowly avoided car accidents, a fire alarm that pulled him out of a lab minutes before a gas leak. He knew it was irrational. People survived near misses all the time, but the theory stayed in the back of his mind. One night, he wrote a program to simulate branching timelines. It wasn't detailed. Each event had two possible outcomes, survive or not. At each step, the program split into two paths. He coded the view of the observer as always following the path that continued. The simulation produced timelines that stretched longer and longer. Some ended quickly. Others carried on for hundreds of steps. But in every case, the thread he followed never stopped. He called it the survivor path. He started thinking about aging, illness, accidents, each one a risk, each one a potential quantum event. The theory didn't promise comfort. In fact, it offered the opposite. You might survive everything, but only in versions of reality where the outcomes became more and more unlikely. A survivor might live into old age, but suffer isolation, pain, or confusion as the world drifted further from what they once knew. He imagined a very old man, alone in a hospital room, long past the normal limits of life. Machines keep failing, systems shut down, doctors leave, but he remains, not out of will, but because his path refuses to end. Every version that leads to unconsciousness is no longer his. He only experiences the ones that stretch on. He told Mira about the simulation. She said she had built something similar, but she had stopped when she realized where it led. Neither of them could disprove the theory. It was consistent with the mathematics, but it opened a door they weren't sure they wanted to walk through. Eli found a journal entry from a few years back. In it, he had written that life had meaning because it ended, that mortality gave shape to existence. He looked at those words and felt unsure. What if death was only something others experienced? What if the self always slipped through? He began reading personal accounts of survivors, people who had walked away from plane crashes, from surgery gone wrong, from sudden medical failures. He wasn't looking for proof, just patterns. He wanted to understand what survival felt like from the inside. One story stood out. A man described a car accident. He had seen the truck coming. He knew there was no time. But he woke up in the hospital, barely scratched. No one could explain how. The police were shocked. They said the impact should have been fatal. The man said it felt like reality skipped a frame, like he was somewhere else, just before the crash. Eli marked that story. He didn't use it as evidence, but it stayed with him. In his lectures, Eli stayed focused on classical interpretations. He explained quantum mechanics through wave functions, superposition, and collapse. He told students that interpretations were tools, not truths. But when the class ended and the room emptied, he sometimes stared at the board and thought about the other paths, the ones where he didn't make it through the day. He imagined those branches continuing without him. They were real in the many-worlds sense, but his experience never reached them. It always returned to the version where he was still here, breathing, thinking, watching time stretch forward. He didn't know if that was a gift or a trap. He only knew that so far, the survivor path had never broken. Erin worked at a small observatory in New Mexico. Most of her nights were spent monitoring signals from deep space, watching for patterns in the radiation that passed near distant black holes. The job was quiet, long hours, cold coffee, but she liked it. It gave her time to think. She had studied physics in college. She'd been drawn in by the big questions. What is time? What is space? What happens when you fall into a black hole? One question always came back to her. What happens to information that crosses the event horizon? The event horizon is the boundary around a black hole. Once something passes it, there's no way back. Not for light, not for anything. That much is clear in the physics. But what about the information that object held? Its structure, its makeup, the quantum details that make it what it is. If a star falls into a black hole, is its information gone forever? Erin remembered a professor once saying, in physics, information should never be destroyed. That was a principle built into the math. If you know the state of a system at one time, you should, in theory, be able to calculate both its past and future. That's what made physics predictable. Even in quantum mechanics, where outcomes are probabilistic, the evolution of a quantum state is still unitary. It preserves information, so why would a black hole be any different? The problem begins when you combine general relativity and quantum mechanics. Relativity describes gravity, space, and time. It tells you that mass bends space. A black hole is what you get when mass collapses under its own gravity to a point so dense that nothing escapes. But quantum mechanics looks at the world on very small scales. Particles, fields, probabilities. When the two theories meet, especially near the event horizon, things get strange. In the 1970s, Stephen Hawking showed that black holes aren't completely black. Due to quantum effects near the event horizon, they emit a faint glow. This radiation comes from particle pairs forming near the horizon. One falls in, the other escapes. The result is slow evaporation. Over time, the black hole loses mass. That's where the paradox appears. If the black hole eventually evaporates through Hawking radiation, and the only thing it releases is this radiation, what happens to the information about what fell in? The radiation looks random. It doesn't seem to carry the imprint of the objects swallowed by the black hole. A chair, a spaceship, a star, Hawking's equations said it didn't matter. The radiation looked the same. This creates a conflict. Quantum theory says information must be preserved, but the process of black hole evaporation suggests it's erased. You're left with a paradox. Either information is destroyed, or something in our theory is wrong. Erin thought about this a lot. She imagined a person falling into a black hole. Not in some dramatic sci-fi way, but in a simplified model. No tidal forces tearing them apart, just a smooth crossing of the event horizon. To an outside observer, time slows down for the falling person. From the outside, it looks like they freeze just before crossing the horizon. But from their perspective, they fall straight through. Eventually, they reach the singularity, a point where our understanding of space and time breaks down. But long before that happens, the outside observer sees something else. The black hole starts to shrink. Over billions of years, it radiates away, slowly, steadily, until it disappears. So the question is, does the information go with it? Some physicists have suggested that the information leaks out through the Hawking radiation. Maybe it's not as random as it seems. Maybe it carries hidden structure. That would preserve information. But we haven't found a way to show that in the math with full certainty. Others propose that the information never really entered the black hole, that it's somehow encoded on the event horizon itself. This idea comes from the holographic principle. It says that all the information about a volume of space can be described by information on its boundary. Think of a hologram. A two-dimensional surface carries the data to create a three-dimensional image. In black hole physics, this would mean that the event horizon acts like a screen. Anything that falls in gets recorded there, not as a picture, but as quantum information. Over time, as the black hole evaporates, that information might get released bit by bit in the radiation. That view fits with work done on string theory and quantum gravity. In particular, studies on something called the ESCFT correspondence, a mathematical framework that connects gravity in a curved space with a quantum field theory on its boundary. In this framework, black holes don't destroy information. They process it, they scramble it, distort it, but eventually release it. Aaron found that idea satisfying, not just because it solved the paradox, but because it kept the rules of physics intact. She liked the idea that no matter how strange the universe was, it didn't cheat. But the debate wasn't settled. Some physicists introduced new possibilities. One was the idea of firewalls. If the event horizon isn't smooth, but a wall of high-energy particles, then anything falling in would be incinerated immediately. That would protect information, but break the smooth passage predicted by general relativity. It would also violate the principle of equivalence, which says that free fall should feel the same as floating in empty space. Firewalls would be a radical change. Others pushed for more modest answers. Maybe black holes don't quite evaporate completely. Maybe they leave behind a remnant, a small, dense object that stores the lost information. But remnants raise other problems. How would they store that much data? Would they be stable? And how would we detect them? Erin once tried to model black hole evaporation using a simplified system in her software. She set up particle interactions near an artificial event horizon. She tracked what came out, what stayed in. Her model was basic, but even there she saw how easy it was to lose track of the original state. The radiation patterns looked thermal, uniform, featureless. She imagined a library falling into a black hole, 1,000 books. Every page, every sentence, gone. The black hole shrinks. In its place, we get a long stream of radiation. No sign of chapters or titles. No way to reconstruct what fell in. If the universe worked like that, it would be like burning a book and losing not just the pages, but the idea of the book. In a physical sense, that violated everything quantum mechanics stood for. She leaned back in her chair. The telescope continued to collect data. Somewhere, a black hole was bending light and warping space. Erin couldn't see what went past the horizon. No one could. That was the whole point. But she could ask the question. Could keep turning the paradox over in her mind. A hole that swallows everything and yet cannot erase what it consumes. A boundary that hides but remembers. A universe that demands information survive, even if we never see how. Nico was a quiet undergraduate who preferred code over conversation. He studied computer science, spent long nights in the lab, and rarely checked his phone. Most of his free time went into building compilers and reading about theoretical machines that had never been built. He didn't like group projects or presentations. He liked puzzles, logic, and answers that either worked or didn't. One afternoon, Nico sat in a small seminar class about computability. The professor, an older man with sharp gestures and a calm voice, wrote 2 words on the board: halting problem. He turned around and said, "This is where things stop being about what computers can do and start being about what they can't." Nico didn't move, but he was listening. The problem starts with a simple idea. Write a program that checks other programs. Feed it some code and some input, and it tells you whether that program will stop or keep running forever. Call this new program a halting checker. At first, it seems possible. After all, computers follow rules. If you know what a piece of code does, why wouldn't you be able to predict if it ever stops? But that's where the problem starts. The professor gave an example. Imagine a simple program that takes in another program as input and then simulates it. If the simulated program stops, our checker returns halts. If the simulated program runs forever, the checker returns loops. It seems logical. You feed the checker some code, and it tells you what that code will do. Clean, useful, and powerful. Now imagine taking that checker and feeding it into itself. That's when the room got quiet. Some students furrowed their brows. Others tried to write it out. The professor continued. Suppose we write a new program that uses this checker, but flips the output. If the checker says the program halts, then this new program runs forever. If the checker says the program runs forever, then this new program halts. Now feed this new program into itself. It creates a contradiction. If the checker says it halts, then it must loop. If the checker says it loops, then it must halt. Either answer leads to the opposite behavior. The logic breaks. The checker cannot exist. Nico had seen recursion before. He had written programs that called themselves. He had used break conditions to stop infinite loops. But this was different. This wasn't a bug in a specific program. It was a limit on what any program could do. He started sketching out the problem in his notebook. He drew a box labeled checker, then another box labeled flipped program. He drew arrows between them. Input goes in, results come out. But when he fed the flipped program into itself, the arrows circled, the boxes looped. There was no stable outcome. It reminded him of a mirror facing another mirror. The image repeats, smaller each time, but never reaches an end. The professor mentioned Alan Turing, a mathematician who worked this out in the 1930s. Turing showed that no general algorithm can decide for all possible programs and inputs whether the program will eventually stop. Some programs halt, some don't, but there is no universal machine that can check them all. Nico wrote that down. No universal checker. He thought about it in terms of tools. If you had a hammer, you could hit nails. If you had a wrench, you could turn bolts. But the halting problem said you could never have a tool that works on every kind of problem like this. Some tasks are beyond computation. He wondered how that applied to real code. What about when compilers warn you that your function might not return? What about static analyzers that predict possible bugs? They seemed to answer this question already. But the professor explained the difference. Those tools work by making safe guesses. They can check specific cases. They use time limits, pattern matching, or conservative estimates. But they can't solve the halting problem in general. Not for every possible input. Not with complete certainty. At some point, they must give up or risk being wrong. Nico ran with the idea. He imagined writing a program called Inspector. Inspector takes any other program and input and says whether it halts. Now write another program called Inverter. It uses Inspector. If Inspector says halt, Inverter loops. If Inspector says loop, Inverter halts. Now feed Inverter into itself. What happens? If Inspector says Inverter halts, then Inverter loops. But if Inspector says Inverter loops, then Inverter halts. Either way, Inspector gets it wrong. The contradiction proves that Inspector cannot be right in every case. That's the core of the halting problem. Nico realized it wasn't just a programming issue. It was a limit of logic itself, a boundary of what any formal system could do. Just like the liar paradox, this sentence is false, the halting problem turned back on itself and collapsed. He thought about writing a program that tried to beat the halting problem, maybe a neural network, maybe a machine that simulated millions of paths and guessed the outcome. But he saw the trap. Guessing was not the same as knowing. Probabilities didn't solve the paradox, they only postponed it. Nico started seeing examples everywhere. A text editor that never finishes loading a huge file, a server that hangs when handling a rare input, an AI model that keeps refining its output and never commits. These weren't just bugs, they were signs of undecidability. You could test, monitor, and predict, but you could never guarantee that any arbitrary process would stop. Not always, not with full certainty. That was the halting problem's power. It marked a limit. Some students found the problem frustrating. They wanted a fix, a patch, a way to write around it. Nico felt something different. He liked the clarity of it. It told you where the line was. It didn't move. It didn't cheat. It said this you cannot do, no matter how clever you are. He remembered reading about Gödel's incompleteness theorems. In those theorems, the structure of arithmetic leads to statements that are true but unprovable. The halting problem worked the same way. The structure of computation leads to problems that are solvable in some cases, but not in all. There is no universal method. Nico stayed after class. He didn't ask a question. He just wanted to sit with the idea a little longer. He opened his laptop and began writing a small piece of code that looped forever, just a few lines. A function that called itself with no end condition. He ran it. It did nothing but consume time. He stopped the process manually. Then he wrote another function. This one stopped after 10 steps. He compared them. One looped, one halted. He could see the difference here. But he also knew that no tool, no matter how advanced, could check every possible version he might write. He sat back and stared at the screen. The halting problem wasn't a failure. It was a feature. A quiet reminder that some answers live outside the reach of machines. Elias spent his time working with old computers. He restored them, kept them running, and studied how they processed information. His small lab at the edge of campus looked more like a museum than a workspace. On the shelves sat machines from every decade since the 1940s. Some still booted, others served as artifacts of what computing used to be. His main research focus wasn't old hardware, though. He studied the limits of what computers could do. He wanted to know not just how machines worked, but what kinds of problems they could never solve. This brought him back again and again to the work of Alan Turing. Turing had shown that there are limits to computation. Some problems are undecidable. No matter how fast your computer runs or how clever your algorithm is, there are tasks it simply cannot finish. The most famous example is the halting problem. You give a machine a program and ask if it will ever stop or run forever. There is no general method that works for all possible programs. Turing proved that. Elias respected those boundaries. They gave structure to the field. But he was also interested in the edge cases, the places where theory stretched. He began reading about machines that could go beyond the Turing limit. The papers called them hypercomputers. A hypercomputer, in theory, can do things no Turing machine can. It can solve the halting problem. It can decide whether any given program will finish or run forever. It can compute things that ordinary machines will never touch. These ideas sounded impossible, but Elias wanted to understand them on their own terms. The first model he studied was the oracle machine. This was a Turing machine with access to an oracle, a kind of black box that could instantly answer specific questions, like whether a given program halts. The oracle didn't explain how it got the answer, it just gave it. With this extra power, the machine could solve problems that standard machines could not. But Elias knew that oracles were abstract, they didn't exist in practice. The point of them was to describe what would be possible if you could access something beyond normal computation. It was like giving a calculator access to a magic button that answered any yes or no question about the future. Then he read about accelerating machines. These were hypothetical models that completed each step of a process faster than the one before. The first step might take 1 second, the next one half a second, then a quarter, then an eighth, and so on. After 2 seconds, the machine would have completed an infinite number of steps. This was called a Zeno machine. Elias found the idea strange but consistent. In math, a series of times like 1 + 1/2 + 1/4 does converge to a finite limit. That means the total time needed to run all those steps is still finite. So in theory, a Zeno machine could run forever in just 2 seconds. With that kind of machine, you could test every possible input for a problem, all in a bounded time. That included checking whether a program ever halts. But then the practical problems came in. Elias thought through the mechanics. Every step would have to be twice as fast as the one before. Eventually, you would hit the limits of hardware, then physics. No signal travels instantly. No processor can act in 0 time. You would need infinite processing speed and no delay. Nature doesn't seem to allow that. Still, he liked that the idea didn't collapse right away. The logic held, even if the reality didn't. Another form of hypercomputation came from infinite time Turing machines. These extended the regular model of computation into transfinite steps. In this system, a machine doesn't stop at step 1 million or 1 billion. It can keep running past every finite step, reaching what mathematicians call omega, an infinite ordinal. At step omega, the machine checks what happened at all earlier steps and continues from there. This kind of machine can do more than a normal one. It can decide some problems that Turing machines cannot. For example, it can solve the halting problem for all standard programs. That's because it has infinite time to test every possibility. But it doesn't stop there. These machines can enter a new kind of computation that keeps going beyond any finite bound. Elias drew diagrams on his whiteboard. He mapped out timelines for these machines. One line showed a Turing machine reaching its limit and stopping. The next showed a Zeno machine completing more and more steps in shrinking time windows. The third showed an infinite time Turing machine passing through layers of infinity, each one building on the last. He knew none of this was physical. But the question that kept him going was whether it had to be. What if the limits of Turing computation weren't the limits of nature, but just the limits of our models? Some physicists had explored that idea. They had asked whether time itself could support infinite computation. If the universe allowed Zeno-style processes, if space could shrink forever, or if black holes could bend time in the right way, maybe these ideas could move from theory to reality. But so far, no one had found evidence that this was possible. Every attempt hit physical barriers, energy limits, quantum noise, thermal problems. The models remained mathematical. Elias didn't mind. He thought of hypercomputation as a mirror. It showed what happened when you pushed a model past its breaking point. It forced you to define your assumptions. It also revealed how much of our trust in computers came from what they couldn't do. He started teaching a seminar on the topic. Each week, he gave his students a different kind of hypercomputer and asked them to explore it. One week, it was Oracle machines. The next, Zeno machines. After that, infinite time models. The goal wasn't to build them. It was to understand what they revealed about computation itself. Some students resisted. They wanted to build things, not think about impossibilities. But others were drawn to the edge of theory. They saw that by understanding what lay beyond computation, they understood computation better. One student, Nina, asked a question that stayed with Elias. She said, "If we can imagine a machine that solves uncomputable problems, what does that say about problems themselves? Are they always tied to machines?" Elias answered carefully. A problem becomes uncomputable because of how we define machines. If you change the machine, you change the boundary. But you still need rules. Without rules, you don't have a machine, you have noise. In that way, hypercomputation was both more and less than people thought. It wasn't about building miracle devices. It was about tracing the edge of what rules could do. Back in his lab, surrounded by machines that once seemed powerful but were now outdated, Elias thought about that edge. Every device had its time. But the questions stayed. Could a machine reach beyond Turing's line if given infinite time? Could logic break its own wall? No answer came, but he kept asking. That was the point. Elena worked in a research lab that focused on theoretical computer science. Her job was to simulate abstract machines on computers. The machines she worked with weren't built out of wires or chips. They were made from ideas. At the center of her work stood the concept of the Turing machine. A Turing machine is simple in structure. It has a long tape that stretches infinitely in both directions. The tape is divided into cells, and each cell holds either a 0 or a 1. The machine reads one cell at a time. It can write a new symbol, move left or right, and switch to a different state. It follows a list of rules. Each rule tells it what to do when it sees a certain symbol in a certain state. Elena had built hundreds of these machines using simulation software. Most of them were small, with just a few states. She would write the rules, run the machine, and watch it either halt or continue forever. Some machines stopped quickly. Others ran for thousands of steps before halting. A few never stopped at all. One day, her advisor told her to study the busy Beaver function. She had heard of it before, but never looked at it closely. It sounded harmless. The name made it seem like a children's toy or a cartoon character. But as she read more, she realized it was one of the most extreme functions ever studied. The busy Beaver function asks a simple question. For a Turing machine with a fixed number of states, what is the maximum number of ones it can write on the tape before it halts? The rules are strict. The machine starts with a blank tape. It can only use zeros and ones. It must stop eventually. Among all machines that follow those rules, which one writes the most ones? This number is called the busy Beaver value for that number of states. At first, the numbers looked reasonable. With one state, the best machine writes 1 1. With 2 states, the best machine writes 4 1s. But then things changed fast. With 3 states, the number jumps to 6. With 4 states, it becomes 13. For 5 states, the value is unknown, but we know it's more than 40,000. For 6 states, the machine runs so long that nobody has ever seen it finish. It may write billions or trillions of ones, but no one can say exactly how many. The growth of the busy Beaver function is unlike anything else. It increases faster than any function you can describe using an algorithm. That includes exponential functions, factorial functions, even functions that stack exponents or factorials. The busy Beaver function outruns them all. It is not just fast, it is uncomputable. Elena found this idea difficult to accept. In her work, computers solved problems with speed and precision. They handled massive data sets and ran simulations for hours without error. But this function sat outside of that. You could describe the function, you could define it, but you could not compute it for even modest values of input. She ran experiments to see it in action. She started with machines that had 2 or 3 states. These were easy to test. They stopped after a few hundred steps at most. She wrote a loop to generate all possible machines with 3 states. The program tried each one, tracked how many ones it wrote, and recorded the result. After a few minutes, she had a list of outcomes. One machine stood out. It wrote 6 ones before halting. That was the busy beaver for 3 states. Then she moved to 4 states. The number of machines grew quickly. There were thousands to test. Most machines halted after a few steps or went into infinite loops. But one machine ran for over 100,000 steps and left 13 ones on the tape before stopping. That was the best found so far. At 5 states, things became impossible. She tried a few machines, but many ran for so long that her computer froze. Others showed no sign of stopping after hours of computation. She realized why the value for 5 states was only known as a lower bound. It was known to be at least 40,000, but nobody knew if that was the best. Elena wrote down a list of functions on the board. Linear, quadratic, exponential, factorial, tetration. All of them had clear growth patterns. All of them could be written as algorithms. All of them failed to match the growth of the busy beaver function. This made her uneasy. She had studied complexity theory. She knew about functions that grew fast. But the busy beaver was not just fast, it was unreachable. No program, no matter how clever, could compute it for all inputs. She thought about the implications. If you could compute the busy beaver function for all inputs, you could solve the halting problem. The halting problem asks where a given Turing machine will ever stop. Alan Turing proved that no general algorithm can answer that question for all machines. But the busy beaver function is tied directly to halting. To find the machine that writes the most ones, you must test all machines that halt. That means you must know which ones halt and which ones don't. So computing the busy beaver function for every input would mean solving the halting problem. Since the halting problem is undecidable, so is the busy beaver function. It's not just hard to compute, it's impossible in the general case. Elena started seeing the paradox. The function is well defined. For any number of states, there is a single correct busy beaver value. The problem is not vague. The rules are clear. But we cannot reach the answer. Not because we lack power or time, but because the question crosses a boundary in computation. The function stands on a sharp edge. It invites you to try. It teases you with early progress. Then it overwhelms every method you use. The growth becomes unmanageable. The search space becomes too large. And worst of all, some machines never halt, and you can never be sure which ones those are. She imagined a Turing machine with 6 states that ran for 1 trillion steps before halting. How would you know it ever stops? You would need to run it forever or find a way to prove it. But many such machines look like they run forever, only to stop after enormous delays. There is no reliable signal. Elena wrote a note in her journal. It said, "Some functions break the boundary between what we can define and what we can know." The busy beaver paradox became more than a math problem to her. It was a mirror of the limits of knowledge, a line that divides structure from chaos. Machines that follow simple rules create outcomes beyond reach, not by randomness, but by logic taken to its edge. She shut down her computer for the night. The last simulation still ran in the background, a 5-state machine that had already consumed over 2 million steps without halting. She didn't stop it, she let it run. Elias played chess every morning before work. He sat at a wooden table by the window in his small apartment, the board always set, the pieces always in place. He liked the structure. 16 pieces per side, 64 squares, patterns he knew, strategies he trusted. The rules felt clean, limited, and complete. One morning, while browsing online forums about endgames, he came across a thread titled "Chess on an Infinite Board." He clicked. The first post described a version of the game with no edges. The board stretched endlessly in every direction, no corners, no sides, just a perfect grid continuing forever. Elias paused. He had never thought about chess that way. The board was always 8 by 8. That was part of its beauty. You learned where the action would happen. You understood the space. The idea of no limits unsettled him. He kept reading. In infinite chess, the standard rules still applied. Each piece moved the same way. Pawns still advanced forward, bishops still traveled diagonally, and kings still moved one square in any direction. But now there was no boundary, no back rank, no edge of the board. He tried to picture a game like that. A knight could jump endlessly in any direction. A rook could move straight ahead for hundreds of squares. A bishop could slide diagonally into the distance and never reach a wall. The queen could command a line stretching far beyond sight. He imagined a pawn advancing forever, never reaching promotion. What did an endgame mean if there was no edge? Could you win? Could you lose? Could you draw if the center of play scattered beyond recovery? Elias printed out a blank grid and drew a small cluster in the middle. 2 kings, a few pawns, 1 rook. He expanded the grid slowly with more paper, adding squares outward. The pieces looked isolated now. They no longer felt contained. The space swallowed them. He read more about the idea. Mathematicians had studied infinite chess as a kind of logic problem. They used it to explore questions about strategy that normal chess didn't allow. In traditional chess, you could calculate every legal position. There were a huge number of possibilities, but they were finite. With infinite chess, that was no longer true. You couldn't list all positions. You couldn't even define the board fully with standard notation. Some people asked whether it was possible to force a checkmate in this version of the game. Not in a practical sense, but in a logical one. They meant whether, from a given position, you could say for sure that one player would win if both played perfectly. In many cases, the answer was yes. Even in the vast space of infinite boards, some positions still allowed checkmate in a finite number of moves. Mathematicians used ordinal numbers to count how many moves were needed. Sometimes it was 10, sometimes it was 50. Sometimes it was more than any whole number you could name. Elias learned about a special kind of position where a player could force a win, but only after a number of moves described by a transfinite ordinal. The count of moves wasn't infinite in the way we usually think of it. It was defined using logical steps, one after another, with no practical way to finish. Not in real life, not on an actual board. But in theory, the win was there. He stopped to think about that. A game you could win, but not finish. A strategy you could understand, but never complete. He wondered how you would play such a game. Where would you start? What would your first move be? If your opponent's king was 1,000 squares away, would you try to close the gap? Or would you build your pieces into a fortress and wait? He set up a new board on paper. This time, he gave white a queen and a king, and black only a king. In regular chess, that was a basic checkmate. But on an infinite board, black's king could be far away, dozens or hundreds of squares. The white king and queen would need to coordinate their approach across a growing distance. The checkmate was still possible, but the number of moves could stretch far beyond what any person could handle. He thought about tempo. In chess, each move mattered. Time had weight. But on an infinite board, time and distance became blurry. You might spend 20 moves just getting your queen into position, then 20 more moving your king into place. Your opponent might not be able to stop you, but they could run. They could flee across the open grid, dodging checkmate as long as possible. Elias looked up and realized an hour had passed. He wasn't sure what to make of it. Infinite chess felt like a mirror. It showed the game's rules pushed to their limits. It kept the same pieces, the same movements, but removed the frame. That one change broke everything he thought he knew. He had always seen chess as a problem with boundaries. You calculated within those boundaries. You mastered positions because they were fixed. You knew how far a bishop could go. You knew where the pawn would promote. You used that knowledge to build plans. Now none of that was guaranteed. In infinite chess, there was always more space. Every plan could be delayed. Every threat could be avoided, not by defense, but by escape. You could keep moving away. Not indefinitely in practice, but logically, yes. That was the power of the infinite board. It offered no final edge. The opponent might trap you eventually, but they would need a perfect strategy that spanned an endless field. Elias thought about drawing. In regular chess, 3-fold repetition or 50 moves without a pawn move meant a draw. But what counted as repetition on an infinite board? If you returned to a square after wandering thousands of moves, was that the same position? And what did 50 moves mean when you were playing a game that could last forever? He saw how these questions weren't just about chess. They were about systems, about logic, about what changes when you remove limits. The rules didn't need to change, but the outcomes did. Possibility became too large to measure. Even simple goals, like checkmate, turned into long, uncertain paths. He opened a fresh page in his notebook and wrote, "Checkmate exists, but may not be reachable." That was the heart of it. The goal remained the same, but the journey no longer had a clear shape. You could follow the rules, make perfect moves, and still find yourself chasing shadows across the board. Elias closed his notebook and looked at his chessboard by the window. It now looked small, even fragile. 64 squares. So much strategy, so much history, but also so much control. The infinite board removed that control. It exposed how structure gave meaning to the game. Without borders, the same rules led to uncertainty. He didn't stop playing regular chess, but the idea stayed with him. He saw each move differently now. Each edge square felt like a comfort, not a limit. Each endgame felt like a closure, not a chase. The infinite board taught him that boundaries were not just constraints. They were also what made the game playable, what made it human. Lena worked with language. She was a logician, but her main interest was not numbers or equations. It was structure, how statements fit together, how meaning built itself from patterns. She liked puzzles, but not just for fun. She believed language revealed the edges of what could be known. One afternoon, she sat in her office surrounded by notes. A half-finished whiteboard showed a long list of sentences, numbered in red marker. Each one said something similar. She read them aloud, more out of habit than need. Statement 1. All statements after this one are false. Statement 2. All statements after this one are false. Statement 3. All statements after this one are false, and so on. She had listed 20 of them, but she knew the pattern continued. The sequence had no end. She could keep writing them forever. That was the point. She leaned back and looked at the board. The structure was simple, but the behavior wasn't. None of the sentences referred to themselves. That was important. This wasn't like the liar paradox, where a single sentence says, "This sentence is false." That version turned on itself. It was self-reference, a kind of linguistic loop. But this was different. Each sentence only pointed forward. It talked about the rest, about the ones that followed, never itself. That detail mattered. She started testing truth values. Suppose statement 1 is true, then all the statements after it must be false. That would mean statement 2 is false. But statement 2 says all following statements are false. If it's false, then not all following statements are false. So at least one of them must be true. But we already decided that all statements after statement 1 are false. That's a contradiction. So statement 1 can't be true. It must be false. Now look at statement 2. If statement 1 is false, we're allowed to consider statement 2 without conflict. Suppose statement 2 is true, then all statements after it must be false. That would make statement 3 false. Statement 3 says all following statements are false. If it's false, then at least one after it must be true. But we already claimed they were all false, because statement 2 was true. Another contradiction. Statement 2 cannot be true, so it must also be false. She followed this reasoning down the list. Each time she assumed a statement was true, it forced the next one to be false. But that in turn created a contradiction unless one of the later statements was actually true, which couldn't happen because each one built on the next in the same way. She started thinking of the sequence as a line of dominoes that never ends. Each one said the rest would fall. But when you tried to push the first, the motion never completed. The fall never began, because the trigger always depended on what lay ahead, and what lay ahead depended on the next, and so on. The fall deferred itself forever. She wrote a note in the margin of her notebook. Infinite dependence, no closure. This paradox didn't rely on a sentence pointing to itself. That made it different from other known paradoxes. No loop. No direct contradiction in a single statement. Instead, the contradiction appeared when the structure as a whole was examined. It was distributed, spread across an infinite sequence. That structure made it feel more stable at first glance. Each statement was clean, logical, grammatically simple, but taken together, they refused to settle. She tried to imagine the sequence as a long line of people. Each one stood in a hallway. Each turned to the people behind them and said, "Everyone behind me is lying." But none looked at themselves. They just pointed backward. If the first person told the truth, then all others lied. But that couldn't be, because if the second person lied, then at least one person behind them told the truth, which would mean the third person, or someone further back, was honest. But that would make the second person's statement partially true, not completely false, and the contradiction returned. She liked this framing, a room of people pointing fingers but never at themselves, a chain of blame never landing anywhere. She walked to the whiteboard again and wrote down a simplified version. Statement N. All statements after N are false. Each new statement added to the problem. With a finite list, the issue dissolved. If there were only 2 statements, you could test each combination. But with an infinite list, the problem stayed open. You could never reach the final statement. There was no end, so you could never confirm that the last one was false and work backward. There was no ground to build on. She opened a logic textbook and looked at the section on semantic paradoxes. Most well-known paradoxes used some form of self-reference. But here was a structure that avoided it entirely and still created instability. Michael Yablo had shown this formally in the 1990s. His paradox proved that contradiction could arise without circular reference, just infinite descent. She thought of this as a descent without foundation, a staircase that never hits the ground. Every step rests on the next. None can bear weight. She wanted to test this in a program. She imagined writing a function for each statement. Each one would check the truth value of all the functions that came after it, but no function would call itself. It would always delegate. Yet when she ran the program, it would never return a result. Because to check the truth of the first function, the program needed the truth of the second, and so on, forever. There would be no base case, no resolution, only deferral. She found that elegant. Not just because it was clever, but because it mirrored real problems in logic and computation. Systems that depend on future steps with no grounding fail to complete. They hang. This type of paradox showed that instability could emerge even from simple, linear language, not from tricks or loops, not from self-denial, just from endless layering. It made her think of truth as a structure that needed roots. You couldn't build it from the top down forever. At some point, you had to touch the ground. She returned to her desk and wrote a final version of the paradox in plain text. 100 statements, numbered from 1 to 100, each saying that all statements after it were false. Then she crossed out the last one, number 100. Without it, the rest stayed open. With it, the cycle completed and broke. But there was no way to finish the list. That was the key. She didn't need to include herself to cause trouble. All she needed was a long enough line of sentences that each leaned on the next, with no bottom. The weight of the paradox was carried not by what the statements said about themselves, but what they refused to say. The silence at the end of the list made all the noise. She leaned back again and looked at the list. It was quiet in the room, the kind of quiet that let thoughts settle. Then she erased the board and started again from statement 1.